If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. Jupiter, the gas giant that dominates our solar system, is more than just a massive ball of swirling storms. It's a celestial wonder that holds secrets of the universe, surrounded by a family of moons that could redefine our understanding of life and planetary evolution. Let's dive into the mysteries and marvels of Jupiter and its incredible moons. This colossal planet, over 300 times the mass of Earth, is essentially a failed star. Its composition of hydrogen and helium mirrors that of the Sun, yet it lacks the mass to ignite nuclear fusion. However, Jupiter's magnetic field, the strongest of any planet in our solar system, rivals the energy of small stars. This invisible shield not only protects its moons, but also generates awe-inspiring auroras that would dwarf Earth's northern lights. Imagine skies illuminated by arcs of light so vibrant they could be seen from space, a cosmic dance of charged particles interacting with its atmosphere. But Jupiter's storms are the true showstoppers. The Great Red Spot, a hurricane-like tempest that has raged for centuries, is a mystery unto itself. Bigger than Earth, this storm offers a glimpse into Jupiter's turbulent atmosphere, where winds can reach speeds of up to 400 miles per hour. Recent studies reveal the storm is shrinking, adding urgency to understanding its origins and fate. What causes such a monstrous storm to persist for so long? And what secrets might it hold about planetary weather systems across the cosmos? While Jupiter itself is captivating, its entourage of moons takes the intrigue to another level. Europa, for instance, is a frozen world that harbors a subsurface ocean beneath its icy crust. Scientists believe this ocean contains more water than all of Earth's oceans combined, making Europa one of the prime candidates in the search for extraterrestrial life. Evidence of geysers erupting from its surface suggests that this hidden ocean interacts with the moon's rocky core, creating conditions that could support microbial life. Could Europa be the next frontier for exploring alien ecosystems? Io, another of Jupiter's moons, is a volcanic powerhouse. With over 400 active volcanoes, it is the most geologically active body in the solar system. These volcanoes are fueled by tidal forces exerted by Jupiter's immense gravity, which stretch and compress Io's surface, generating heat. The result is a landscape so dynamic it changes in real time, with lava flows reshaping its surface almost constantly. If we were to visit Io, we'd witness a world in perpetual motion, with plumes of sulfur and molten rock shooting miles into space. Callisto, on the other hand, presents a different story. Heavily cratered and ancient, it's like a time capsule preserving the early history of the solar system. Unlike Europa or Io, Callisto's surface is calm, marked by impact craters rather than geological upheaval. Beneath its icy exterior, however, there's a growing suspicion of a hidden ocean. If confirmed, Callisto would join the ranks of moons that could potentially harbor life, showing us that even seemingly desolate places can hide secrets beneath their surfaces. Then there's Ganymede, the largest moon in the solar system, bigger even than Mercury. It's the only moon known to generate its magnetic field, a phenomenon that still puzzles scientists. Ganymede's surface is a blend of ice and rock, with grooves and ridges suggesting tectonic activity in its distant past. Like its siblings, Ganymede may also hide a subsurface ocean, expanding the possibility that Jupiter's moons form a system teeming with opportunities for discovery. Jupiter's role as the solar system's guardian cannot be overlooked. Its immense gravity acts as a cosmic shield, deflecting asteroids and comets that might otherwise strike Earth. Yet, it also serves as a trap for such objects, creating a complex system of Trojan asteroids that share its orbit. These remnants from the early solar system are like fossils, preserving clues about the chaotic period of planetary formation. Modern missions like NASA's Juno spacecraft have given us an unprecedented view of Jupiter. Juno's close-up observations have revealed intricate details of its polar cyclones, magnetic field, and deep atmospheric dynamics. But the journey doesn't stop there. Upcoming missions like the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper aim to explore the icy moons of Jupiter more closely. These missions are poised to revolutionize our understanding of these distant worlds, potentially answering questions about their habitability and the evolution of the solar system. Jupiter and its moons are not just celestial bodies. They are keys to understanding fundamental questions about life, the universe, and everything in between. From the violent storms of its atmosphere to the hidden oceans beneath its moons, Jupiter is a testament to the boundless wonders of the cosmos. As we continue to study this gas giant and its companions, we edge closer to unraveling the mysteries of our own origins and the possibilities of life beyond Earth. In the vast expanse of space, Jupiter stands as a reminder of both the beauty and the enigma of the universe. As we venture deeper into Jupiter's influence, we uncover how its gravitational dominance has sculpted not only its moons, but also the broader architecture of the solar system. This massive planet, often called a cosmic vacuum cleaner, has a profound effect on the paths of comets and asteroids, steering some into stable orbits and hurling others far from the sun. This interplay between chaos and order exemplifies Jupiter's dual nature as both protector and potential threat. It's a stark reminder of the balance required to sustain life on a fragile planet like Earth. The gas giant's gravitational power has also given rise to its spectacular ring system. Though less prominent than Saturn's, Jupiter's rings are no less fascinating. These faint, dusty arcs were likely formed from the debris of shattered moons or captured asteroids. They are a subtle yet profound feature, representing the remnants of celestial collisions that hint at a violent past. Observing them closely might reveal more about the early solar system's chaotic beginnings, where impacts and migrations shaped the planets we know today. Jupiter's influence extends even further when considering its Trojan asteroids. These clusters of rocky objects share Jupiter's orbit, one group leading the planet and another trailing behind. Thought to be remnants of the primordial solar system, these asteroids serve as time capsules, preserving material from the era of planetary formation. Missions like NASA's Lucy spacecraft aim to visit these ancient relics, providing insights into the chemistry and conditions that existed billions of years ago. The exploration of Jupiter and its moons has a direct impact on how we search for exoplanets. As scientists examine the gas giant's dynamic atmosphere, magnetic fields, and diverse moons, they develop tools and theories that are applied to studying distant worlds. For instance, the discovery of exoplanets in hot Jupiter systems, gas giants orbiting perilously close to their stars, has forced astronomers to rethink the formation and migration of planets. Could the secrets of Jupiter help us decode the mysteries of these alien systems, some of which may host conditions ripe for life? Europa, in particular, has inspired comparisons to potentially habitable exoplanets. If life exists beneath its icy shell, it could serve as a model for similar environments light years away. The idea of a global ocean insulated by ice, warmed by tidal forces, and rich in chemical interactions has transformed how we approach the search for extraterrestrial life. It's no longer a question of if we'll find such conditions beyond our solar system, but when. Europa's intrigue doesn't just reside in its potential for life, but in how it shapes our aspirations to explore. Technological advancements are key to unlocking these mysteries. Spacecraft like Juno have demonstrated the incredible potential of modern instruments, from infrared imaging that peers through thick cloud layers to magnetometers that map the structure of magnetic fields. These tools have not only advanced our understanding of Jupiter, but have also paved the way for future missions, equipping us with the ability to investigate other gas giants like Saturn, Uranus, and Neptune with unprecedented precision. While Jupiter's moons dominate the conversation about potential habitability, even the planet itself has some surprising possibilities. Theoretically, its atmosphere could harbor life forms adapted to extreme conditions, floating in the upper layers where temperatures and pressures are less hostile. Although purely speculative, this idea challenges our preconceptions of where life can exist, pushing us to consider environments far beyond our own terrestrial experience. Cultural and historical perspectives on Jupiter add another layer of fascination. Throughout human history, this bright and imposing planet has inspired myths, religious symbolism, and scientific breakthroughs. The ancient Romans named it after their king of gods, while other cultures viewed it as a harbinger of fortune or doom. Galileo's discovery of its moons in the 17th century marked a turning point in astronomy, challenging the geocentric view of the universe and cementing Jupiter's role as a beacon of discovery. As we contemplate the future of space exploration, Jupiter remains a cornerstone of our ambitions. Colonizing its moons may be a distant dream, but they offer tantalizing prospects for human expansion into the outer solar system. Advanced technologies could enable the construction of habitats on Europa or Callisto, shielded from radiation and equipped to harness the moon's resources. Such endeavors would mark a bold step toward becoming a multi-planetary species, driven by the same curiosity that first led us to gaze at the stars. The gas giant and its moons remind us that the universe is far from static. It's an evolving theater of forces, collisions, and creations, all governed by the laws of physics, yet imbued with an almost poetic sense of purpose. Every storm, volcanic eruption, and hidden ocean tells a story of transformation, one that echoes our own planet's journey and hints at the paths others might take. Jupiter is more than a planet. It's a cosmic laboratory, a gravitational architect, and a source of endless inspiration. Its moons, with their diverse landscapes and potential for life, stand as testaments to the complexity and resilience of celestial bodies. Together, they form a system that challenges our understanding of what's possible and dares us to imagine what lies beyond. With each new mission and discovery, Jupiter and its moons draw us closer to the answers we seek about the universe and our place within it. In their presence, we are reminded of both the grandeur and the humility that space exploration demands. As our journey into the realm of Jupiter and its moons continues, we are compelled to ask deeper questions about the nature of our solar system and the potential connections it has to distant star systems. Jupiter's sheer scale and influence make it a microcosm of astrophysical processes that may play out across the galaxy. By studying it, we are not just learning about our own celestial neighborhood, but are piecing together a broader narrative of planetary systems. One of the most profound aspects of Jupiter's system is the concept of habitability in unexpected places. Traditionally, the search for life focused on Earth-like planets within the so-called habitable zone, where liquid water can exist on the surface. Jupiter's moons, however, challenge that paradigm. Here we have worlds outside the habitable zone, yet their internal heat and complex interactions with Jupiter's gravity provide the energy needed to sustain potentially life-supporting environments. This revelation expands our understanding of where life might arise, urging us to look beyond conventional criteria. Take, for example, the interplay of tidal forces. Europa, Io, and Ganymede are locked in an orbital resonance, a rhythmic gravitational dance that ensures their orbits remain stable while generating immense tidal energy. This energy creates heat within these moons, driving volcanic activity on Io and maintaining liquid water beneath Europa's ice. Such interactions demonstrate that habitability is not solely reliant on proximity to a star. Gravitational relationships can play an equally vital role. This insight has profound implications for exoplanet research, as similar mechanisms could operate in distant planetary systems. Jupiter's magnetic field is another enigma that continues to intrigue scientists. Stretching millions of miles into space, it traps charged particles, forming intense radiation belts. These belts are both a hazard and an opportunity. While they pose significant challenges for spacecraft and potential human exploration, they also act as natural particle accelerators, providing a laboratory for studying high-energy processes. Understanding Jupiter's magnetosphere helps us not only design better missions, but also grasp how magnetic fields shape the environments of exoplanets and even stars. Meanwhile, the chemistry of Jupiter's atmosphere offers clues about the planet's formation and the early solar system. The presence of water, ammonia, methane, and other compounds hints at the primordial materials that coalesced to form the gas giant. Juno's measurements have revealed unexpected variations in these elements, suggesting that Jupiter may have captured materials from beyond its immediate region during its formation. This challenges existing models of planet formation and highlights the dynamic nature of the early solar system. The moons of Jupiter continue to surprise us with their diversity and potential. Beyond the famous 4 Galilean moons, Io, Europa, Ganymede, and Callisto lie dozens of smaller satellites, each with unique characteristics. Some, like Amalthea and Himalaya, are irregularly shaped remnants of ancient collisions. Others may have been captured from the Kuiper Belt, offering a glimpse into the outer reaches of the solar system. Studying these smaller moons not only enriches our knowledge of Jupiter's history, but also provides a window into the processes that govern moon formation and capture across the universe. As humanity prepares for the next phase of exploration, the lessons learned from Jupiter and its moons will play a pivotal role. The development of advanced propulsion systems, radiation shielding, and autonomous robotics will be essential for future missions to these distant worlds. The Europa Clipper mission, set to launch in the coming years, represents a milestone in this endeavor. Equipped with cutting-edge instruments, it will fly close to Europa, analyzing its icy surface, probing its ocean, and searching for signs of life. Similarly, the JUICE mission will focus on Ganymede and Callisto, investigating their potential as habitable worlds. But the exploration of Jupiter is not just about technology, it's also about inspiration. The images returned by Juno and earlier missions, such as Voyager and Galileo, have captivated people worldwide, showcasing the planet's swirling storms, vibrant auroras, and dynamic moons. These visuals remind us of the beauty and complexity of the cosmos, igniting curiosity in new generations of scientists, engineers, and dreamers. Looking even further into the future, the concept of human presence in the Jovian system begins to take shape. While the harsh radiation environment near Jupiter poses significant challenges, the potential for colonization lies in its moons, particularly Callisto. Far enough from Jupiter's radiation belts and rich in resources, Callisto could serve as a stepping stone for humanity's expansion into the outer solar system. A research outpost on Callisto could not only support the study of Jupiter and its moons but also serve as a launch point for missions to Saturn, Uranus, and beyond. Jupiter, with its immense presence and complex system of moons, serves as both a destination and a stepping stone in humanity's quest to explore the cosmos. It embodies the challenges and rewards of pushing beyond our limits, of seeking knowledge not for immediate gain, but for the sheer wonder of discovery. As we unravel its mysteries, we are reminded of the boundless potential of human ingenuity and the infinite possibilities that lie among the stars. In the vast tapestry of the universe, Jupiter is a vibrant thread, a testament to the diversity and richness of the cosmos. Its storms rage, its moons whisper of hidden oceans, and its gravity binds a system that continues to challenge our understanding. As we stand at the edge of this cosmic frontier, Jupiter invites us to look deeper, dream bigger, and never stop exploring. The journey is far from over. In fact, it has only just begun. As we continue to peer into the mysteries of Jupiter, one thing becomes abundantly clear. This gas giant is not just a planet. It is a system, a miniature solar system within our own, with each moon and feature playing a critical role in its ongoing story. The sheer complexity of this system reveals that Jupiter is not merely a celestial body, but a dynamic arena of processes that echo the broader workings of the cosmos. One of the most captivating aspects of Jupiter's system is its capacity to push our understanding of planetary science to its limits. Consider the gravitational tug-of-war that shapes the behavior of its moons. These interactions not only heat their interiors, but also create fascinating orbital resonances, such as the Laplace resonance involving Io, Europa, and Ganymede. This intricate dance ensures that their orbits remain in a precise rhythm, influencing their geological activity and, potentially, their habitability. Such resonances could also be occurring in exoplanetary systems, making Jupiter's moons a prototype for studying distant worlds. Among the moons, Europa continues to captivate scientists and the public alike. Its icy surface, crisscrossed by fractures and ridges, hints at a subsurface ocean brimming with potential. Recent evidence suggests that radiation from Jupiter interacts with salts on Europa's surface, creating unique chemical signatures detectable from afar. These findings are more than just interesting. They are vital clues in the search for life. If we can confirm organic chemistry or energy gradients within Europa's ocean, it could revolutionize our understanding of life's universality in the universe. Io, in stark contrast, is a world of fire and fury. Its volcanic activity, driven by relentless tidal heating, produces lava lakes and sulfurous plumes that tower miles above its surface. Observing Io provides a unique opportunity to study extreme volcanism, offering insights into how similar processes might have shaped early Earth or occur on rocky exoplanets close to their stars. Io's volcanic spectacle is not just a geological curiosity, but a reminder of the raw power that shapes worlds. Ganymede, with its magnetic field and layered interior, raises other tantalizing questions. Could its magnetic interactions with Jupiter's magnetosphere influence the potential habitability of its subsurface ocean? Ganymede's magnetic field creates auroras that dance across its poles, revealing yet another dimension of complexity. These auroras, when studied closely, provide valuable information about the moon's composition, ice layers, and the dynamics of its hidden ocean. Callisto, often overshadowed by its siblings, has its own story to tell. Its heavily cratered surface holds a record of impacts stretching back billions of years, making it a living chronicle of solar system history. If Callisto's suspected ocean exists, it would add yet another dimension to its scientific importance. Unlike the other Galilean moons, Callisto experiences less tidal heating, making its potential ocean a fascinating counterpoint to Europa's and Ganymede's. Could life exist in such a quiet, isolated environment? Exploring Callisto might answer this question, while revealing more about the diversity of habitable environments. Beyond the moons, the very nature of Jupiter's atmosphere offers a lesson in extremes. Beneath its visible clouds lies a world of crushing pressures and rising temperatures. As one descends into the planet's depths, hydrogen gas transitions into a strange metallic form, conducting electricity and generating Jupiter's immense magnetic field. This metallic hydrogen layer, thought to exist only under the most extreme conditions, challenges our understanding of matter and could have implications for studying the interiors of exoplanets and even failed stars. Jupiter's Great Red Spot, while iconic, is just one of many storms churning in its atmosphere. Recent observations show that smaller, long-lived storms, nicknamed brown barges, form and evolve in its equatorial regions. These storms, along with the planet's vibrant cloud bands, hint at deep atmospheric dynamics that remain poorly understood. By studying these systems, we gain insights not only into Jupiter's weather, but also into the behavior of gas giants as a class of planets. The auroras at Jupiter's poles, fueled by interactions with its magnetic field and charged particles, are another breathtaking phenomenon. Unlike Earth's auroras, which are predominantly green due to oxygen, Jupiter's auroras glow in shades of ultraviolet and infrared, producing light shows that defy imagination. These auroras are driven by particles funneled along magnetic field lines from the volcanic moon Io, illustrating the deep interconnectedness of the Jovian system. They also highlight the potential for similar auroral phenomena on exoplanets orbiting close to active stars. Looking to the future, our exploration of Jupiter holds the promise of answering some of the most profound questions about the universe. Missions like Europa Clipper and JUICE represent the first steps toward understanding the habitability of icy worlds, but the potential for robotic landers or even human missions to the Jovian system is on the horizon. Technological advancements in radiation shielding, autonomous exploration, and sustainable energy systems will be critical in making such missions a reality. Imagine a lander descending onto Europa's surface, drilling through its icy crust to sample the ocean below. Picture a probe flying through Io's volcanic plumes, collecting data on its composition and the forces driving its activity. Envision an orbiter mapping Ganymede's magnetic field in unprecedented detail, unraveling the mysteries of its interior. These scenarios are no longer the stuff of science fiction. They are tangible goals that could be achieved within this century. Even more exciting is the possibility of international collaboration in exploring Jupiter and its moons. Just as the International Space Station has united nations in the pursuit of knowledge, a joint mission to the Jovian system could bring together the brightest minds and cutting-edge technology from across the globe. Such an endeavor would not only expand our scientific horizons, but also inspire unity in the face of a shared cosmic goal. Jupiter's system is a gateway, to understanding the universe. It teaches us about the origins of planets, the conditions for life, and the boundless creativity of nature. Each storm, moon, and magnetic ripple holds a piece of a puzzle that connects us to the stars. As we stand on the cusp of new discoveries, we are reminded of the power of exploration, not just to uncover the unknown, but to transform our place in the cosmos. The wonders of Jupiter and its moons are a testament to the infinite possibilities that await us in the vast expanse of space. As we push the boundaries of exploration, Jupiter and its moons continue to stand as a testament to the universe's grandeur and complexity. Every facet of this system invites deeper inquiry, challenging what we know and inspiring new ways of thinking about planetary systems, life, and the processes that govern celestial mechanics. Jupiter's gravitational dominance, often referred to as the solar system's guardian, plays a crucial role in maintaining stability within the inner solar system. Without Jupiter, Earth might have been subjected to far more frequent catastrophic asteroid impacts, potentially derailing the evolution of life. Yet, Jupiter is also a double-edged sword. Its gravitational pull can redirect comets and asteroids into trajectories that bring them perilously close to Earth. This paradox highlights the delicate balance Jupiter strikes in shaping the fate of our planet and its neighbors. In the search for extraterrestrial life, Jupiter's moons remain some of the most promising locations. Europa, with its subsurface ocean protected by a thick shell of ice, offers the tantalizing possibility of an aquatic ecosystem. Recent evidence from telescopic observations and data from the Galileo spacecraft suggests the presence of water vapor plumes erupting from Europa's surface. These plumes provide a unique opportunity to sample its ocean indirectly, bypassing the need to drill through miles of ice. If future missions confirm organic molecules or even microbial life within these plumes, it would represent one of the greatest discoveries in human history. The implications of finding life on Europa extend far beyond our solar system. It would demonstrate that life is not unique to Earth and that similar environments on exoplanets or their moons might also host living organisms. The discovery of even the simplest life forms would shift the paradigm of biology and force us to redefine our understanding of what it means to be alive. Io's volcanic activity, the most extreme in the solar system, continues to offer clues about the interactions between planetary bodies and the immense forces of gravity. Io's ever-changing surface, shaped by constant eruptions, creates a world unlike any other. Observing Io not only helps us understand tidal heating, but also provides insights into how energy from such processes might influence the atmospheres and geology of exoplanets orbiting close to their host stars. These planets, often referred to as hot Jupiters, may have similar internal heating mechanisms driving dynamic atmospheric and surface conditions. Ganymede, with its complex structure and magnetic field, represents a treasure trove for planetary scientists. Its magnetic field suggests a partially molten core, while its icy crust hints at a subsurface ocean potentially rich in dissolved minerals. These factors create a layered environment where water, rock, and energy sources coexist, key ingredients for life. Ganymede's unique position as the only moon with a magnetic field makes it a prime candidate for detailed study, as its interactions with Jupiter's magnetosphere could offer insights into the processes shaping magnetic phenomena across the cosmos. Callisto, often viewed as the quiet sibling of the Galilean moons, stands as an ancient witness to the solar system's early history. Its heavily cratered surface, relatively untouched by geological activity, serves as a record of billions of years of impacts and cosmic events. This makes Callisto an ideal target for studying the primordial conditions of the solar system. If its suspected ocean is confirmed, Callisto could also offer clues about how water-rich environments evolve in low-energy, isolated settings. Jupiter itself continues to defy expectations. The deeper we probe into its atmosphere, the more mysteries we uncover. Its turbulent clouds, swirling storms, and dynamic weather patterns are shaped by processes that are not yet fully understood. Observations from the Juno spacecraft have revealed that Jupiter's atmospheric layers extend far deeper than previously thought, with powerful jet streams influencing its structure on a massive scale. Studying these phenomena helps us refine our models of gas giant planets and contributes to our understanding of atmospheric physics across the galaxy. The Great Red Spot, a storm that has persisted for centuries, continues to shrink and change, puzzling scientists. This iconic feature, once large enough to fit 3 Earths, is gradually diminishing, prompting questions about the longevity of such atmospheric phenomena. Its study provides a unique opportunity to understand the life cycle of planetary storms and may offer insights into the atmospheres of other gas giants, both in our solar system and beyond. As technological advancements accelerate, our ability to explore Jupiter and its moons becomes increasingly sophisticated. The Europa Clipper will carry high-resolution cameras, ice-penetrating radar, and spectrometers capable of identifying the composition of Europa's surface and potential ocean. These tools are designed to answer fundamental questions about the moon's habitability, including whether it has the chemical building blocks necessary for life. Meanwhile, the JUICE mission will focus on Ganymede, Callisto, and Europa, conducting detailed studies of their surfaces, interiors, and interactions with Jupiter's magnetosphere. These missions represent a leap forward in our quest to understand not just the Jovian system, but also the broader dynamics of icy worlds. Looking beyond these missions, the concept of interstellar exploration begins to take shape. The knowledge gained from studying Jupiter and its moons will inform the design of spacecraft capable of reaching exoplanetary systems. By understanding the challenges of navigating and surviving in environments dominated by intense radiation and gravitational forces, we can better prepare for missions to distant stars. Jupiter's system also holds promise as a proving ground for long-term human exploration. Establishing a human presence on one of its moons, such as Callisto, would be an unprecedented achievement, requiring innovations in radiation protection, resource utilization, and sustainable living in extreme environments. Such a base could serve as a hub for scientific research and as a stepping stone for humanity's journey to even more distant destinations. In the end, Jupiter and its moons remind us of the boundless potential for discovery that lies within our reach. They challenge us to think beyond our horizons, to push the limits of what is possible, and to embrace the unknown. Each new revelation about this majestic system deepens our understanding of the universe and our place within it. As we gaze at Jupiter through our telescopes or study its features through the eyes of robotic explorers, we are participating in a legacy of wonder and curiosity that spans generations. The questions Jupiter poses, and the answers it offers, are a testament to the enduring human spirit of exploration. In the vast and infinite cosmos, Jupiter stands as a beacon, calling us to venture further, to dream bigger, and to uncover the secrets of the universe, one discovery at a time. As we set our sights on the future of Jupiter exploration, the boundaries of what we know about the gas giant and its extraordinary moons continue to expand. Each new mission and discovery builds on centuries of curiosity, unlocking secrets that deepen our understanding of the universe and fuel ambitions for interplanetary exploration. With every question answered, new mysteries emerge, reminding us that Jupiter's story is far from complete. One of the next big leaps in understanding Jupiter and its moons will come through advanced robotic missions. The Europa Clipper, set to launch in the near future, represents a monumental step forward in the search for life. Unlike previous spacecraft, which focused on flybys and limited data collection, Europa Clipper will orbit Jupiter and make repeated close passes over Europa, allowing for detailed analysis of its ice-covered surface and potential subsurface ocean. This mission aims to determine the thickness of Europa's ice shell, map its surface in high resolution, and search for the signatures of organic molecules and water plumes that may be erupting from beneath its icy crust. If signs of habitability, or even life, are detected, it will redefine the scope of astrobiology. Europa's icy ocean could become the new benchmark for where scientists search for life, both within our solar system and in exoplanetary systems. The discovery of life in such an environment would suggest that life might be far more common than the previously thought, existing not only on temperate, Earth-like planets but also in hidden, extreme environments far from a star's warm embrace. Europa's exploration will also serve as a stepping stone for future missions, potentially involving landers, or even submarines capable of penetrating its ice and exploring its ocean firsthand. Meanwhile, The JUICE Jupiter Icy Moons Explorer mission, spearheaded by the European Space Agency, will broaden our understanding of the Jovian system as a whole. By studying Ganymede, Callisto, and Europa in detail, JUICE will provide critical insights into the diversity and complexity of icy moons. The mission's focus on Ganymede, the largest moon in the solar system, will be particularly transformative. Ganymede's subsurface ocean, its unique magnetic field, and its potential for tectonic activity make it a fascinating target for understanding planetary processes that might create environments suitable for life. JUICE will also investigate Callisto, a moon often overshadowed by its more famous siblings. Callisto's ancient, heavily cratered surface is like a frozen record of the solar system's earliest days, offering a glimpse into a time when planets and moons were still forming. If its hidden ocean exists, Callisto could challenge assumptions about the conditions needed to maintain liquid water in the outer solar system. Both Europa Clipper and JUICE will pave the way for future exploratory missions to the Jovian system, which may include landers, rovers, and even advanced autonomous systems designed to explore beneath the ice. Concepts like cryobots, robotic probes capable of melting through Europa's ice crust, are already in the conceptual stage. These machines could reach the subsurface ocean, sampling its water and searching for life forms, whether microbial or more complex. Beyond Europa, the extreme volcanic world of Io also demands attention. Io's relentless volcanic activity, driven by tidal forces from Jupiter and its neighboring moons, offers a unique laboratory for understanding how planetary interiors remain geologically active. Future missions to Io might involve orbiters or flybys equipped with advanced instruments to measure the composition of its volcanic plumes, map its dynamic surface, and study how it interacts with Jupiter's powerful magnetosphere. The Jovian system also has broader implications for our understanding of exoplanets. Gas giants like Jupiter are among the most commonly detected planets in other star systems. By studying Jupiter's atmosphere, magnetic field, and gravitational interactions with its moons, scientists can draw parallels to the behavior of exoplanets, especially those in hot Jupiter systems. These findings help refine our models of planetary formation, migration, and the potential habitability of moons or planets orbiting gas giants. Jupiter's immense gravitational influence and its role as a cosmic vacuum cleaner have also inspired discussions about planetary defense. Understanding how Jupiter deflects or captures asteroids and comets can inform strategies to protect Earth from potential impacts. Additionally, the Trojan asteroids, rocky bodies that share Jupiter's orbit, are targets of interest. These ancient objects are remnants from the early solar system and may hold clues about the materials and processes that shaped our planetary neighborhood. Looking even further into the future, the idea of human exploration in the Jovian system becomes an exciting possibility. While the intense radiation near Jupiter makes the planet itself inhospitable, its moons, particularly Callisto, offer more favorable conditions. Callisto's relative distance from Jupiter's radiation belts and its potential resources make it a prime candidate for a human outpost. A base on Callisto could support extended missions, serving as a hub for exploring the Jovian system and testing technologies for deeper space exploration. Such a base would also facilitate the study of Jupiter's magnetic field, its radiation environment, and its interactions with the Sun. These investigations are critical not only for understanding Jupiter, but also for preparing humanity for the challenges of living and working in space environments far from Earth. Advanced technologies such as radiation shielding, closed-loop life support systems, and resource extraction from the moon's surfaces would be essential for these endeavors. Jupiter's influence extends far beyond its immediate vicinity. Its magnetic field interacts with the solar wind, creating a vast magnetosphere that envelopes its moons and reaches into space for millions of miles. Studying this magnetosphere helps us understand how magnetic fields protect planets and their atmospheres, a factor that may influence the habitability of exoplanets and other star systems. By examining Jupiter's interactions with the Sun, scientists can also learn more about how space weather shapes planetary environments, both in our solar system and beyond. The gas giant's enduring mysteries, such as the depth and nature of its great red spot, the behavior of its polar cyclones, and the secrets hidden in its deep atmosphere, continue to drive scientific inquiry. The shrinking of the Great Red Spot raises questions about the life cycle of planetary storms, while the intricate patterns of its polar regions, revealed in stunning detail by the Juno spacecraft, challenge our understanding of fluid dynamics on a massive scale. Jupiter, with its family of diverse and intriguing moons, serves as a reminder of the boundless possibilities within our solar system. It is not merely a planet to study, but a gateway to understanding the broader universe. Its moons, each unique and dynamic, exemplify the variety of environments that might exist in planetary systems across the galaxy. From Europa's icy ocean to Io's fiery surface, from Ganymede's magnetic wonders to Callisto's ancient scars, Jupiter's system encapsulates the extremes of what planetary science can offer. As humanity looks to the stars, Jupiter remains a beacon, urging us to explore, question, and dream. The next generation of explorers, scientists, and visionaries will build on what we learn from this magnificent planet, carrying its lessons to the far reaches of the cosmos. Jupiter is not just a destination. It is an inspiration, a challenge, and a promise of discoveries yet to come. The allure of Jupiter and its moons extends beyond scientific curiosity. It fuels a profound sense of wonder and compels humanity to reach farther into the cosmos. As we continue to investigate this majestic giant and its enigmatic system of satellites, we stand at the precipice of breakthroughs that could redefine our understanding of life, the universe, and our place within it. Future exploration of Jupiter is not limited to robotic missions alone. The concept of interdisciplinary research will play a critical role in unlocking the secrets of the Jovian system. Collaboration between planetary scientists, chemists, physicists, biologists, and engineers will allow us to approach these mysteries from multiple angles. For example, understanding the chemistry of Europa's potential ocean requires expertise in oceanography and microbiology, while unraveling the dynamics of Jupiter's storms demands advanced knowledge of atmospheric physics and fluid dynamics. One particularly exciting area of research is the study of tidal heating across Jupiter's moons. Tidal forces between Jupiter and its moons generate immense amounts of heat, especially in Io and Europa. This heat drives geological activity, melts subsurface ice, and potentially creates environments capable of supporting life. By studying these forces in detail, scientists can refine their models of how energy is distributed in planetary systems, shedding light on the processes that sustain activity in distant exoplanetary systems with multiple moons or planets. The potential for ocean exploration on Europa represents one of the most ambitious goals of planetary science. Concepts like cryobots, autonomous probes capable of melting through Europa's thick ice shell, have captured the imagination of researchers. Equipped with sophisticated sensors, cameras, and even microbial detection systems, such a device could descend into Europa's ocean and provide direct evidence of its composition and habitability. A successful cryobot mission would not only revolutionize our understanding of Europa, but also demonstrate the viability of exploring similar environments on icy exoplanets or moons around gas giants and other systems. Meanwhile, the volcanic eruptions on Io continue to provide an unparalleled opportunity to study extreme geological activity. Io's sulfur-rich plumes, which reach hundreds of kilometers above its surface, contain information about the moon's interior composition and the complex interactions between its crust and mantle. Future missions equipped with spectrometers and imaging devices could fly through these plumes, collecting data that might reveal clues about Io's thermal evolution and its contribution to Jupiter's magnetosphere. Callisto, often viewed as a relatively quiet moon, offers a stark contrast to its more geologically active neighbors. Its heavily cratered surface, untouched by significant geological processes for billions of years, makes it an ideal site for studying the solar system's early history. A future mission to Callisto could analyze its ice and rock composition, providing insights into the primordial materials from which the Jovian system formed. Additionally, Callisto's low radiation environment makes it a strong candidate for a human outpost, a stepping stone for deeper exploration into the outer solar system. Ganymede, the largest moon in the solar system, continues to intrigue scientists with its unique combination of features. Its magnetic field, the only one generated by a moon, raises questions about its internal structure and the presence of a partially molten core. Furthermore, its surface, marked by both older, cratered regions and younger, grooved terrain, suggests a history of tectonic and cryovolcanic activity. Understanding Ganymede's geological past could help us piece together the story of how icy worlds evolve and whether such processes create environments conducive to life. The exploration of Jupiter itself is equally compelling. Juno's mission has revealed a wealth of data about the planet's atmosphere, deep interior, and polar regions. Future missions could take this further by deploying atmospheric probes to descend into Jupiter's cloud layers, measuring pressures, temperatures, and chemical compositions at various depths. Such probes could uncover the secrets of Jupiter's deep atmosphere, including the mysterious transition from gaseous hydrogen to metallic hydrogen, a state of matter rarely observed in nature, but crucial to understanding gas giants' magnetic fields. Jupiter's role as a cosmic protector also warrants further study. Its immense gravity not only deflects comets and asteroids from colliding with Earth, but also captures many of them into its own orbit, creating its Trojan asteroids. These ancient remnants of the early solar system hold clues about the materials that form planets and moons. NASA's Lucy mission, currently underway, will explore these Trojans, offering insights into their composition and origins. As we look further ahead, the development of sustainable space exploration technologies will enable humanity to extend its reach into the Jovian system. Advanced propulsion systems, such as nuclear-powered spacecraft, could reduce travel times and provide the energy needed for extended missions in deep space. Innovations in radiation shielding and autonomous systems will be essential for operating in the high-radiation environment near Jupiter. The possibility of human exploration of the Jovian system is no longer relegated to science fiction. Callisto, with its relative safety from radiation and potential for in-situ resource utilization, stands out as the most viable target for a human base. Such a base could serve as a hub for scientific research, providing insights into the Jovian system while testing technologies needed for interplanetary travel and long-term habitation. This vision of human presence in the Jovian system also sparks questions about the role of humanity in space exploration. As we expand our footprint in the cosmos, we are faced with ethical considerations about the impact of our activities on pristine environments. If we were to discover life on Europa or another moon, how would we ensure that our exploration efforts do not harm these ecosystems? The challenge of balancing scientific progress with the responsibility to preserve alien environments will become a defining issue of future exploration. Ultimately, Jupiter and its moons embody the vast potential of our solar system to inspire, challenge, and transform. They are a reminder that the universe is full of wonders waiting to be discovered, and that every step we take toward understanding them brings us closer to answering humanity's greatest questions. Are we alone? What is our place in the cosmos? And how can the knowledge we gain shape our future? Jupiter's storms will continue to swirl. Its moons will keep their secrets a little while longer. But humanity's journey to unravel these mysteries is unstoppable. With every mission launched, every discovery made, and every question asked, we affirm our role as explorers, not just of our solar system, but of the universe itself. Jupiter is more than a destination. It is a symbol of the endless frontier, urging us onward, one leap at a time. As humanity's gaze remains fixed on Jupiter and its awe-inspiring system, the future of exploration promises to deliver revelations that could forever change our understanding of space, life, and our place in the cosmos. Jupiter and its moons are not just celestial objects to be studied. They are part of a vast narrative of creation, evolution, and potential habitability that extends beyond our solar system and into the far reaches of the galaxy. The next phase of exploration could involve autonomous swarms of robotic probes, designed to operate collaboratively in the harsh environments of Jupiter's system. These swarms could be deployed to explore multiple moons simultaneously, sharing data and adapting to challenges in real time. Such missions would allow scientists to investigate the unique environments of Io, Europa, Ganymede, and Callisto with unprecedented efficiency, uncovering links between their geological, atmospheric, and magnetic characteristics. In particular, Europa's plumes remain a tantalizing target for direct sampling. Flying a spacecraft through these plumes to capture and analyze their material would provide the clearest evidence yet of the moon's potential to host life. These samples could reveal the chemical makeup of Europa's subsurface ocean, including the presence of organic compounds, salts, and other elements critical to life as we know it. The data collected could also help refine our understanding of the moon's oceanic dynamics, including whether hydrothermal vents, similar to those on Earth's ocean floor, might provide the energy needed to sustain ecosystems. Meanwhile, Ganymede's magnetic field and internal structure offer a unique opportunity to study the evolution of icy moons. Future missions could deploy magnetometers and ground-penetrating radar to create detailed maps of its interior, identifying layers of ice, liquid water, and rock. These studies might reveal the presence of pockets of liquid water closer to the surface than previously thought, potentially increasing the moon's habitability. Io, with its constant volcanic activity, offers a natural laboratory for studying how extreme geological processes shape a moon's surface and atmosphere. Future spacecraft could monitor Io's volcanic plumes and lava flows in real time, using high-resolution imaging and spectroscopy to understand the moon's internal heat generation and the effects of tidal forces from Jupiter. These observations would not only illuminate Io's unique characteristics, but also provide insights into volcanic processes on exoplanets and other rocky bodies in the universe. Beyond the moons, the study of Jupiter's atmosphere will remain a priority. While Juno has already provided extraordinary insights into the gas giant's polar cyclones and deep atmospheric layers, future missions could deploy advanced atmospheric entry probes capable of surviving longer and diving deeper into Jupiter's storms. These probes could measure the transitions between its layers, revealing how heat, pressure, and turbulence interact to create its iconic banded appearance and its colossal storms. Jupiter's auroras, among the most powerful in the solar system, continue to fascinate scientists. These light shows are driven by charged particles funneled along Jupiter's immense magnetic field, interacting with its upper atmosphere. Observing these auroras at various wavelengths, from ultraviolet to infrared, will help us better understand how magnetic fields influence planetary atmospheres, a phenomenon that could have implications for studying exoplanets with strong magnetic fields. As missions like Europa Clipper and JUICE lay the groundwork, future efforts may focus on the use of nuclear-powered ice penetrators or cryobots to access subsurface oceans directly. These technologies, though still in development, represent the next frontier in planetary exploration. A cryobot equipped with sensors and cameras could travel through the ice of Europa or Ganymede, sampling water and searching for signs of microbial life or other bioindicators. Such missions could fundamentally alter our understanding of where life can exist and the diversity of ecosystems that might thrive beyond Earth. In addition to robotic exploration, human missions to the Jovian system are a long-term goal that will require breakthroughs in technology and engineering. A manned mission to Callisto, for instance, would be a historic milestone in humanity's expansion into the outer solar system. Callisto's relatively low radiation levels and stable surface make it an ideal candidate for a research outpost. From such a base, astronauts could remotely operate rovers and drones across the other moons, conduct in-depth studies of Jupiter's magnetic field, and test technologies needed for even deeper space exploration. Beyond the scientific and technological challenges, exploring Jupiter and its moons also inspires profound philosophical and ethical questions. If life is discovered on Europa, how will humanity respond? Should we alter our exploration strategies to protect such ecosystems, or will the pursuit of knowledge take precedence? These questions demand careful consideration, as they touch on the broader implications of our role as stewards of the universe. The study of Jupiter also holds lessons for understanding our own planet. By comparing Jupiter's storms, atmospheric dynamics, and magnetic field with Earth's, scientists can gain insights into similar processes occurring here, such as the behavior of hurricanes, jet streams, and auroras. These comparisons deepen our appreciation of the interconnectedness of planetary systems and the universality of physical laws across the cosmos. Perhaps most profoundly, the exploration of Jupiter and its moons reinforces a fundamental truth. The universe is a place of infinite diversity, filled with environments and phenomena that challenge our assumptions and expand our imagination. Whether it's the swirling chaos of Jupiter's Great Red Spot the fiery eruptions of Io, the hidden ocean of Europa, or the ancient scars of Callisto, each feature tells a story of transformation and resilience. As humanity embarks on this next chapter of exploration, Jupiter stands as a beacon of possibility. Its system of moons, dynamic atmosphere, and immense magnetic field remind us that the universe is far richer and more complex than we could ever imagine. With each step forward, we uncover new layers of meaning and wonder, pushing the boundaries of what it means to explore. The journey to understand Jupiter is not just about science. It's about humanity's unquenchable thirst for discovery, our drive to seek out the unknown, and our capacity to dream. Jupiter is more than a planet. It is a symbol of the vast, untapped potential of the cosmos and an invitation to continue reaching for the stars. As our exploration of Jupiter and its moons advances, we find ourselves standing on the threshold of discoveries that promise to reshape our understanding of the cosmos. Jupiter, with its colossal presence and dynamic system of moons, represents an endless source of wonder and a reminder that the universe's most profound secrets often lie in the most extreme and unexpected places. The upcoming decades will likely see the rise of in-situ exploration technologies capable of penetrating environments that were previously inaccessible. Europa's thick ice shell, long seen as a barrier, could become a gateway to one of the most promising sites for extraterrestrial life. Innovations like laser-heated drills or cryobots with built-in sensors may allow humanity to probe the icy depths, reaching Europa's liquid ocean and sampling its waters for signs of life. These missions would require unprecedented levels of precision, ingenuity, and collaboration, but the potential rewards, discovering alien life, would redefine humanity's place in the cosmos. Jupiter's vast magnetic field, the strongest in the solar system, remains an enigmatic force shaping not just the planet, but its entire system. Future missions equipped with highly sensitive magnetometers could map the intricate dynamics of this field in even greater detail, revealing how it interacts with charged particles, the solar wind, and the magnetic fields of its moons. Understanding this interaction could provide insights into the magnetic environments of exoplanets, particularly those orbiting close to their stars, where magnetic fields might play a critical role in atmospheric retention and habitability. The Great Red Spot, Jupiter's iconic storm, continues to fascinate scientists and the public alike. This centuries-old tempest, while shrinking in size, remains a testament to the planet's extreme weather systems. Observations from upcoming spacecraft could delve deeper into the mechanisms driving this storm, analyzing its internal structure and the chemical processes sustaining it. Such studies might also shed light on why the Great Red Spot is shrinking and whether new, equally massive storms could form in the future. Meanwhile, Io's volcanic activity offers an unparalleled opportunity to study geological processes under extreme tidal forces. By deploying orbiters or landers specifically designed to withstand Io's harsh environment, future missions could capture real-time data on its ever-changing surface. Monitoring the interactions between Io's volcanoes and Jupiter's magnetosphere could also reveal how moons contribute to the formation of planetary magnetic fields and their auroras, a phenomenon that has implications for understanding magnetospheres across the galaxy. Ganymede's unique features continue to present some of the most exciting opportunities for exploration. As the only moon known to generate its magnetic field, Ganymede offers a natural laboratory for studying the internal dynamics of icy worlds. Future missions could focus on its subsurface ocean, mapping its depth, salinity, and the processes that keep it in a liquid state. The discovery of tectonic activity on Ganymede would add another layer of complexity, suggesting that even distant, icy moons can exhibit geological processes similar to those on Earth. The moons of Jupiter also hold significant promise for understanding the potential for resource utilization in space exploration. Callisto, with its ancient, cratered surface, could become a testing ground for technologies that extract water ice, minerals, and other resources necessary for sustaining human presence in deep space. These resources could support long-term missions in the Jovian system, or even serve as waypoints for ventures further out to Saturn, Uranus, and beyond. As we contemplate the possibility of human exploration in the Jovian system, radiation shielding and advanced life support systems will become critical priorities. Jupiter's intense radiation environment poses one of the greatest challenges to both robotic and human missions. Developing materials and technologies capable of withstanding this radiation will not only enable exploration of Jupiter's moons, but also advance the feasibility of human habitats on other worlds, such as Mars or the Moon. The study of Jupiter and its moons is not just a scientific endeavor. It is a profound exercise in understanding the diversity of planetary systems. Gas giants like Jupiter are among the most common types of planets found in the galaxy, often accompanied by multiple moons. By studying Jupiter's system, we are effectively building a blueprint for interpreting exoplanetary systems and identifying environments that could support life. For instance, tidal heating, a phenomenon observed in the interactions between Jupiter and its moons, is likely to occur in many exoplanetary systems with similar configurations. Understanding how tidal forces generate heat and sustain geological activity on Io or Europa provides critical insights into how distant moons or planets might remain active and potentially habitable even if they orbit far from their stars. The possibility of life in Jupiter's system also forces us to confront profound philosophical questions. If microbial or even complex life exists on Europa or another moon, what ethical obligations do we have to protect these ecosystems? How would such a discovery influence humanity's self-perception and our understanding of life's prevalence in the universe? These questions go beyond science, touching on the realms of philosophy, ethics, and even theology. Jupiter, with its swirling storms, glowing auroras, and diverse moons, serves as a cosmic classroom for humanity. Every mission, every discovery, and every question it raises teaches us something new, not just about the universe but about ourselves. The challenges of exploring Jupiter drive technological innovation, foster international collaboration, and ignite the imagination of people worldwide. As we stand on the brink of the next great age of exploration, Jupiter beckons us with its mysteries and its promise. It is a reminder that the universe is vast, filled with wonders we have yet to comprehend, and that the pursuit of knowledge is an unending journey. With each step we take toward understanding Jupiter, we come closer to unraveling the story of the cosmos and our place within it. The path forward will not be easy, but it will be worth every challenge, every question, and every discovery. Jupiter and its moons are calling, and humanity is ready to answer. In the spirit of exploration, innovation, and discovery, we will continue to journey into the unknown, driven by the same curiosity that first led us to gaze at the stars and wonder what lies beyond. Jupiter's legacy will be one of inspiration, a testament to what we can achieve when we dare to dream beyond our horizons. The exploration of Jupiter and its captivating system of moons represents more than a scientific pursuit. It is a journey into the unknown, a quest to uncover the secrets of a distant world that has shaped the evolution of our solar system. With each passing decade, the technological and intellectual advancements bring us closer to unraveling the mysteries of this gas giant and its extraordinary companions. As the curtain rises on the next era of exploration, we are poised to expand the frontiers of knowledge in ways once deemed impossible. One of the most groundbreaking areas of future research will center on Europa's subsurface ocean, where conditions may resemble those found in Earth's deep-sea hydrothermal vent ecosystems. Missions like Europa Clipper are just the beginning. Subsequent exploration could deploy landers equipped with ice-penetrating drills capable of extracting samples from beneath the surface. These landers might also house autonomous submersibles, designed to swim through Europa's dark, alien waters, searching for traces of microbial life or evidence of complex biological activity. The importance of such discoveries cannot be overstated. The confirmation of life in Europa's ocean would be a paradigm-shifting event, proving that life can arise and persist in environments radically different from those on Earth. It would suggest that life may be a common phenomenon throughout the universe, thriving wherever water, energy, and the right chemical ingredients converge. Meanwhile, Io's volcanic landscape offers unparalleled opportunities for understanding the dynamics of planetary interiors under extreme tidal forces. Future missions might focus on deploying orbiters to map Io's surface in unprecedented detail, tracking the evolution of its volcanic eruptions over time. The data gathered could help scientists understand how tidal heating operates and why Io's geological activity is so much more intense than any other moon in the solar system. These insights might even inform theories about the volcanic activity of exoplanets, especially those orbiting close to their stars. Ganymede's magnetic field, a unique feature among moons, remains a puzzle. Its existence suggests that Ganymede has a partially molten core, which generates the dynamo effect responsible for its magnetic activity. Missions that probe Ganymede's internal structure could clarify how such processes arise in icy worlds and whether similar conditions might exist elsewhere in the galaxy. Ganymede's suspected subsurface ocean also presents exciting possibilities for habitability, with studies focusing on whether heat and nutrients from the moon's core could sustain life in isolated environments. On Callisto, the ancient, cratered surface serves as a time capsule, preserving a record of the solar system's early history. Future exploration might prioritize landing on Callisto to study its geology and measure its internal structure. Such a mission could determine whether Callisto's subsurface harbors a liquid ocean and, if so, how such an isolated body of water has remained stable over billions of years. The moon's low radiation levels also make it an attractive target for human exploration, with potential plans to establish a research outpost there as humanity's first step into the outer solar system. While the moons draw much of the attention, Jupiter itself remains a source of enduring intrigue. Its massive atmosphere, with layers of swirling clouds and powerful jet streams, is a natural laboratory for studying the physics of gas giants. Future missions might deploy atmospheric probes capable of descending into Jupiter's lower layers, where pressures soar and temperatures climb to unimaginable levels. These probes could help scientists understand the composition and behavior of metallic hydrogen, a substance thought to exist in Jupiter's interior and crucial to the generation of its immense magnetic field. Jupiter's Great Red Spot, shrinking and evolving over time, continues to challenge our understanding of long-lived atmospheric phenomena. New missions could use advanced imaging and spectroscopy to probe the storm's depths, unraveling the secrets of its longevity and revealing the forces that sustain its incredible energy. These studies may also illuminate broader patterns of atmospheric behavior that apply not just to Jupiter, but to other gas giants and exoplanets with thick atmospheres. The planet's auroras, among the most powerful in the solar system, offer another fascinating avenue for exploration. Unlike Earth's auroras, which are primarily driven by solar wind interactions, Jupiter's are influenced by its immense magnetic field and the volcanic activity of Io. Observing these auroras across multiple wavelengths could help scientists understand how magnetic fields interact with planetary atmospheres, a process that could shape the habitability of planets and moons across the cosmos. As humanity looks beyond Jupiter, the Jovian system serves as a template for studying exoplanetary systems. Many of the gas giants discovered in other star systems are similar in size and composition to Jupiter, and some are believed to host extensive systems of moons. By studying Jupiter's interactions with its moons and its environment, we refine our ability to interpret the data from distant exoplanetary systems and assess their potential to support life. In the long term, the exploration of Jupiter and its moons will demand revolutionary advances in technology. Nuclear-powered spacecraft capable of extended operations in the shadowed, radiation-heavy regions of the Jovian system will be essential. Innovations in autonomous systems and artificial intelligence will enable probes to make decisions in real time, adapting to unforeseen challenges and maximizing scientific returns. The idea of human exploration in the Jovian system, once confined to the realm of science fiction, is becoming a tangible possibility. Establishing a human presence on Callisto could serve as a stepping stone for even more ambitious missions to Saturn and beyond. Such an outpost would require robust life support systems, radiation shielding, and the ability to extract and utilize local resources, such as water ice for drinking, oxygen production, and fuel. But the journey to Jupiter is not just about reaching a destination. It is about expanding humanity's horizons and embracing the unknown. Jupiter and its moons challenge us to think creatively, act boldly, and push the limits of what is possible. They are a reminder that exploration is as much about the journey as it is about the discoveries, a process that transforms not just our understanding of the universe but also ourselves. The legacy of Jupiter's exploration will be one of inspiration and discovery. It will remind us that even in a universe filled with challenges and mysteries, the human spirit of curiosity and determination can overcome the impossible. Jupiter's system, with its storms, oceans, volcanoes, and ancient landscapes, calls to us, inviting us to explore, learn, and dream. The adventure has only just begun. As the adventure of exploring Jupiter and its extraordinary moons unfolds, humanity's focus on this immense gas giant sharpens, revealing a future rich with discovery, innovation, and profound questions about the cosmos. Jupiter's system is not only a treasure trove of scientific opportunities, but also a stage for testing the resilience of our technology, the depth of our knowledge, and the extent of our imagination. The evolution of space exploration missions will be pivotal in the coming decades. Beyond Europa Clipper and JUICE, concepts for future spacecraft are becoming increasingly ambitious, incorporating breakthroughs in propulsion, AI, and remote sensing. These missions aim to do more than just observe. They aspire to interact with and analyze the Jovian environment in ways that were once thought impossible. For example, Io volcanic plume samplers could revolutionize our understanding of this moon's dynamic geological activity. By flying directly through volcanic ejecta, such probes could capture samples of molten rock and gases, helping scientists determine the composition of Io's interior. These missions would illuminate the complex relationships between Jupiter's tidal forces and Io's volcanic activity, offering insights that could extend to other volcanically active worlds in the galaxy. Similarly, subsurface ocean explorers could go far beyond surface-level investigations of Europa, Ganymede, and Callisto. Technologies under development, such as autonomous cryobots and hydrothermal vent probes, are designed to penetrate ice layers and navigate liquid environments beneath the surface. These explorers would be equipped with advanced instruments capable of detecting organic molecules, isotopic ratios, and energy gradients, all indicators of potential life. A successful mission of this kind would mark one of humanity's greatest scientific achievements. On the surface of these moons, long-duration landers could provide a wealth of data. A lander on Europa, for instance, could deploy seismic instruments to measure ice movement and detect activity in the ocean below. Similarly, a Ganymede lander might investigate the moon's unique magnetic field directly, while a Callisto outpost could analyze its geology to understand its role in the early solar system. Meanwhile, Jupiter itself remains a cornerstone of planetary science. The planet's deep interior holds answers to fundamental questions about gas giant formation, not just in our solar system, but throughout the galaxy. Future missions could use gravity measurements and magnetic field mapping to probe the transition between Jupiter's outer layers and its dense metallic hydrogen core. Understanding how and where heat flows through Jupiter's layers could also explain the planet's remarkable atmospheric patterns, including its persistent jet streams and banded structure. The mystery of the Great Red Spot also continues to intrigue scientists. What sustains this enormous storm? Why has it persisted for centuries? And why is it now shrinking? By deploying atmospheric probes capable of descending into the storm itself, researchers could uncover the mechanisms driving its longevity. Such studies would also enhance our understanding of atmospheric dynamics on exoplanets with similar gas giant characteristics. The role of magnetospheres in shaping planetary systems is another area ripe for exploration. Jupiter's magnetosphere, the largest in the solar system, extends far beyond the planet, influencing its moons and even affecting the solar wind. Future spacecraft could map this magnetic field with unprecedented precision, studying how it interacts with charged particles and generates auroras at Jupiter's poles. These findings would deepen our understanding of planetary magnetospheres, which are critical to protecting atmospheres and maintaining surface habitability on distant worlds. As we expand our reach into the Jovian system, the potential for human exploration grows more tangible. Establishing a human outpost on Callisto could serve as the first step toward permanent habitation in the outer solar system. Such a base would require self-sufficient systems capable of producing food, water, and oxygen from local resources. Astronauts could conduct real-time scientific studies, operate remote equipment on other moons, and test the technologies necessary for even longer missions to Saturn or interstellar space. A human presence in the Jovian system would also create opportunities for collaborative international exploration, just as the International Space Station brought nations together to push the boundaries of low Earth orbit. A mission to Callisto or Europa could unite the world in the pursuit of knowledge. The challenges of deep space exploration are too vast for any one country to tackle alone, making the Jovian system a perfect setting for global cooperation. Beyond science and exploration, Jupiter also inspires us to reflect on the broader implications of finding life beyond Earth. If microbial life is discovered on Europa or another moon, how will humanity approach this revelation? What responsibilities do we have to protect such ecosystems from contamination or exploitation? These questions will demand thoughtful, ethical responses as we continue to explore the cosmos. Jupiter's system also holds clues about the origins of the solar system itself. Its immense gravity likely played a role in shaping the formation of the inner planets, influencing their orbits, and even determining which materials coalesced to form Earth. By studying Jupiter and its moons, scientists hope to uncover evidence of the chaotic early solar system, when collisions and migrations sculpted the planetary landscape we see today. As humanity ventures deeper into the Jovian system, public engagement and inspiration will play a vital role. Images of Europa's icy plains, Io's fiery eruptions, and Jupiter's swirling storms captivate people worldwide, fostering a sense of connection to the cosmos. These missions remind us of the power of exploration to unite, educate, and inspire. They show us that even in a universe filled with challenges, there is always more to learn, more to discover, and more to dream. Jupiter and its moons are not just celestial objects. They are a testament to the boundless creativity of the cosmos. They challenge us to think beyond the familiar, to embrace the unknown, and to strive for answers to questions that have yet to be asked. With every step forward, we honor the legacy of explorers who dared to look up at the night sky and wonder what lay beyond. The journey to Jupiter is more than a scientific endeavor. It is a celebration of humanity's insatiable curiosity, our relentless pursuit of knowledge, and our unyielding determination to uncover the mysteries of the universe. As we continue this journey, Jupiter will remain a beacon, guiding us into the vast, uncharted expanse of space and reminding us of the infinite possibilities that await. The exploration of Jupiter and its moons embodies humanity's pursuit of answers to the most profound questions about our existence, the origins of life, and the nature of the universe. Each discovery deepens our understanding while unveiling even more mysteries, ensuring that the Jovian system remains a focus of scientific inquiry and inspiration for generations to come. The role of Jupiter as a solar system architect cannot be overstated. Its immense gravitational pull has not only shaped the orbits of nearby planets and moons, but also influenced the asteroid belt and the delivery of water and organic materials to Earth during its formative years. Future missions could investigate how Jupiter's interactions with comets and asteroids might have contributed to Earth's habitability. Spacecraft sent to study Jupiter's Trojan asteroids, such as NASA's Lucy mission, are poised to uncover remnants of the primordial building blocks of the solar system, providing critical insights into its chaotic early days. As we develop the tools and technologies to explore Jupiter, new mission concepts are emerging that aim to overcome the challenges of its extreme environment. These include autonomous drones capable of navigating the harsh radiation belts around the planet, and advanced subsurface probes designed to penetrate the thick ice shells of its moons. By pairing these technologies with sophisticated AI, future missions could operate independently, adapting to unforeseen challenges and optimizing scientific returns without direct human control. Among the moons, Europa remains a centerpiece in the search for life. While upcoming missions like Europa Clipper will perform detailed reconnaissance, the dream of sending a cryobot or hydrobot to its subsurface ocean continues to inspire engineers and scientists. Concepts for such missions envision a multi-stage approach, an orbiter mapping the surface and identifying a landing site, followed by a lander deploying a cryobot to melt through the ice, and ultimately, a hydrobot exploring the ocean itself. These systems might one day be capable of detecting microbial life, mapping underwater ecosystems, or even recording the sounds of Europa's hidden seas. Ganymede and Callisto, though often less discussed than Europa, are equally fascinating targets. Ganymede's subsurface ocean, coupled with its magnetic field, makes it a natural laboratory for understanding the dynamics of icy moons. If Ganymede's ocean interacts with its rocky core, as Europa's might, it could harbor the same chemical gradients that sustain life on Earth. Future missions could explore these interactions while also investigating the source of Ganymede's magnetic field, a feature unique among moons. Callisto, with its ancient and undisturbed surface, is an intriguing contrast to its geologically active siblings. If its suspected subsurface ocean exists, Callisto could provide a critical comparison point for understanding how such oceans form and persist in less dynamically heated environments. Additionally, Callisto's low radiation environment makes it the most suitable candidate for a human presence, where a research outpost could facilitate studies of the Jovian system and test technologies for deep space exploration. Io, the most volcanically active body in the solar system, represents an extreme that pushes our understanding of planetary geology to its limits. Future missions might focus on capturing high-resolution data on Io's volcanic eruptions, understanding the processes driving its incredible heat output, and studying how its volcanic materials interact with Jupiter's magnetosphere. Such research has implications far beyond Io, shedding light on tidal heating processes that might occur on exoplanets and moons across the galaxy. The potential for resource utilization in the Jovian system is also becoming a significant consideration for future exploration. Water ice on Europa, Ganymede, and Callisto could provide essential supplies for human missions, while other materials, such as salts and minerals, might be extracted to support long-term habitation or fuel production. Developing these capabilities would represent a significant leap toward humanity's ability to sustain itself in deep space. Jupiter itself, with its massive atmosphere and unique internal structure, continues to present some of the most compelling questions in planetary science. The behavior of metallic hydrogen, thought to exist in Jupiter's depths, remains one of the least understood phenomena in planetary physics. Probing these layers with advanced atmospheric entry vehicles or remotely sensing the planet's interior could provide answers about the conditions that give rise to gas giants and their magnetic fields. The study of Jupiter's polar cyclones, revealed in stunning detail by the Juno mission, opens new avenues for understanding atmospheric dynamics on a massive scale. These cyclones, which form intricate geometric patterns at the poles, challenge our understanding of how weather systems behave in extreme conditions. Observing these features over time could reveal how they form, evolve, and interact with the planet's broader atmospheric circulation. As we refine our understanding of Jupiter, its connections to exoplanetary systems become increasingly apparent. Gas giants like Jupiter are among the most commonly detected exoplanets, often orbiting close to their stars in configurations known as hot Jupiters. While these exoplanets differ significantly from Jupiter in temperature and proximity to their stars, studying our own gas giant provides a foundational framework for interpreting data from distant worlds. Insights into Jupiter's formation, migration, and interactions with its moons are shaping theories about how planetary systems develop across the galaxy. The philosophical implications of exploring Jupiter and its moons are profound. If life is discovered, whether microbial or something more complex, on Europa, Ganymede, or elsewhere, it would force us to confront our understanding of life's uniqueness and resilience. Such a discovery would raise ethical questions about our responsibilities toward these ecosystems and how we balance exploration with preservation. Public engagement will also play a critical role in this ongoing exploration. Images of Jupiter's swirling storms, Io's volcanic plumes, and Europa's icy surface have already captured the imagination of millions. As new missions return even more detailed data, the stories they tell will inspire the next generation of scientists, engineers, and dreamers to continue humanity's journey into the cosmos. Jupiter and its moons symbolize both the challenges and the rewards of space exploration. They push the boundaries of what we can achieve technologically, intellectually, and creatively. The Jovian system is a testament to the complexity and beauty of the universe, a reminder that every question answered reveals new mysteries, and a call to embrace the unknown with courage and curiosity. As humanity sets its sights ever farther into the cosmos, Jupiter will remain a guiding light, a planet of storms, moons, and infinite possibilities. The adventure has only just begun, and the discoveries awaiting us promise to be as transformative as the first steps taken by those who dared to look beyond our world and into the vastness of space. Jupiter, in all its grandeur, stands as a monument to the power of exploration and the enduring quest to understand the universe and our place within it. As humanity's gaze continues to focus on Jupiter, it becomes increasingly clear that this massive gas giant and its extraordinary moons represent the perfect intersection of science, technology, and the boundless human desire to explore. Jupiter is not just a destination. It is a canvas upon which the universe paints some of its most intricate and dynamic phenomena. The road ahead is one of discovery, transformation, and deep introspection as we unlock the secrets of this celestial titan. The exploration of Europa's icy ocean remains at the forefront of our efforts. One of the most revolutionary concepts in development is the deployment of autonomous underwater rovers, robots capable of navigating the hidden ocean beneath Europa's icy crust. These machines would be equipped with advanced chemical analyzers, cameras, and biosensors designed to detect traces of organic compounds, microbial life, or energy sources. The ocean floor, potentially dotted with hydrothermal vents, could be an oasis of biological activity, much like Earth's deep-sea ecosystems. To complement such missions, orbiters and ice-penetrating radars will map Europa's surface and internal structure with unprecedented precision. These observations could identify thin spots in the ice, where future landers might most effectively drill through to the ocean below. A systematic approach to exploring Europa's ocean could uncover not just the potential for life, but also its underlying mechanisms, how energy and chemistry work together to sustain it. On Io, the most volcanically active body in the solar system, missions might aim to measure the forces driving its extreme geological activity. High-resolution mapping of its surface and real-time observation of volcanic eruptions could provide insights into the immense tidal forces exerted by Jupiter and neighboring moons. Io's continuous resurfacing offers a glimpse into processes that likely shaped the early Earth and may still occur on distant exoplanets experiencing similar tidal stresses. Ganymede's unique magnetic field, a rarity among moons, continues to intrigue scientists. As the largest moon in the solar system, Ganymede offers a case study in the evolution of icy worlds with dynamic interiors. Its subsurface ocean, layered beneath a thick ice crust, might interact with its rocky mantle and core, creating conditions that sustain life. By deploying landers and magnetometers, we could measure the properties of Ganymede's magnetic field and investigate its internal structure, piecing together how such a field arises in icy environments. Meanwhile, Callisto's ancient surface, unmarred by tectonic activity, stands as a silent witness to billions of years of solar system history. This moon, with its low radiation levels, offers an opportunity to study the impacts and cosmic events that shaped the Jovian system in its earliest days. Callisto's suspected subsurface ocean could also serve as a testing ground for understanding how isolated bodies of liquid water evolve and whether they might harbor life. At Jupiter itself, the mysteries of the Great Red Spot and polar cyclones demand further exploration. The Great Red Spot's shrinking size and changing dynamics challenge our understanding of long-lived atmospheric systems. Meanwhile, Jupiter's polar regions, with their striking geometric cyclone patterns, offer a rare glimpse into the behavior of fluids under extreme conditions. Deploying long-duration atmospheric probes to study these phenomena could provide invaluable data for comparative studies of exoplanets with thick, dynamic atmospheres. Jupiter's auroras, powered by its immense magnetic field, represent another frontier of research. These glowing displays at the poles are unlike anything seen on Earth, driven by interactions with charged particles from Io and the solar wind. By studying these auroras in detail, we can better understand how magnetic fields influence planetary environments, a key factor in determining the habitability of exoplanets with strong magnetic fields. The Trojan asteroids that share Jupiter's orbit are another target of growing interest. As remnants from the early solar system, These rocky bodies contain clues about the materials and processes that form planets. Missions like Lucy, which will explore these asteroids, could uncover their composition, revealing insights into the building blocks of the solar system and the conditions that existed during its chaotic early years. Looking to the future, the possibility of human exploration in the Jovian system is becoming increasingly realistic. Callisto, with its relatively stable environment and low radiation levels, is the leading candidate for a human outpost. Such a base could serve as a hub for robotic missions to the other moons, enabling scientists to explore the system more efficiently. Astronauts stationed on Callisto could remotely operate landers and drones, minimizing risks while maximizing the reach of exploration. The technological challenges of living and working in the Jovian system are immense. Advanced radiation shielding, self-sustaining habitats, and systems for extracting resources from local materials would be essential. Water ice on Callisto could be converted into drinking water, oxygen, and hydrogen fuel, enabling long-term missions without reliance on resupply from Earth. These technologies would not only support human presence at Jupiter, but also lay the groundwork for further exploration of the outer solar system and beyond. Beyond the scientific and technological implications, the exploration of Jupiter also stirs profound philosophical and ethical questions. If life is discovered on Europa or another moon, how will humanity navigate its responsibilities toward protecting these ecosystems? Should exploration continue, or should such environments remain untouched? These questions will force us to rethink our role as explorers and stewards of the cosmos, balancing our thirst for knowledge with a duty to preserve what we discover. As missions to Jupiter and its moons inspire awe and curiosity, they also have the power to unite humanity. Just as the Apollo program galvanized the world with its promise of exploration and achievement, the search for life and understanding in the Jovian system can foster global collaboration. Nations working together to explore this distant realm will share in the triumphs of discovery, building a legacy of cooperation and shared purpose. Jupiter stands as a symbol of the universe's boundless creativity and complexity. Its storms, moons, and magnetic field remind us that the cosmos is a place of extremes, full of wonders that challenge our assumptions and expand our horizons. The journey to understand Jupiter is not just about unlocking its secrets. It is about pushing the limits of what is possible, embracing the unknown, and daring to dream on a cosmic scale. As we continue this journey, we do so with the knowledge that each step forward brings us closer to answering humanity's most profound questions. Are we alone? What is the nature of life? How did the universe come to be? Jupiter and its moons offer a gateway to these answers, and a reminder that the pursuit of knowledge is an endless, exhilarating adventure. The legacy of Jupiter's exploration will be one of inspiration, discovery, and unity. It will remind us that in a universe filled with challenges, it is our curiosity, resilience, and determination that propel us forward. With Jupiter as our guide, humanity will continue to explore, learn, and dream, venturing ever deeper into the infinite possibilities of the cosmos. As humanity's exploration of Jupiter and its moons advances, the journey extends beyond scientific discovery. It is a profound exercise in redefining our relationship with the cosmos. Jupiter, with its colossal storms, immense gravity, and captivating system of moons, embodies the complexity and beauty of the universe, offering a stage for transformative exploration that will echo through generations. The prospect of integrated exploration strategies for the Jovian system is becoming increasingly feasible. Future missions will likely leverage a combination of orbiters, landers, submersibles, and autonomous drones, each playing a specific role in unraveling the mysteries of Jupiter and its moons. A fully integrated system might involve orbiters scouting for surface features of interest, followed by landers equipped with spectrometers and drills to investigate those sites in detail. Drones could be deployed to map rugged terrains, and cryobots would take the plunge into subsurface oceans, pushing the boundaries of exploration to places that have never been reached. A key target of these strategies will remain Europa's ocean, where the potential for life is most tantalizing. Advances in synthetic biology and bioengineering might one day allow us to design biosensors capable of detecting even trace amounts of organic molecules in Europa's waters. If signs of life are found, subsequent missions could focus on detailed sampling and analysis, even returning samples to Earth for comprehensive study. However, Europa is just one chapter of the Jovian story. Io, with its hyperactive geology, offers a glimpse into volcanic processes driven to extremes. Missions equipped with heat-resistant probes could investigate the mechanics of Io's lava lakes and vents, analyzing how such environments might influence the Moon's thin atmosphere and interaction with Jupiter's magnetic field. This research could illuminate similar processes on rocky exoplanets close to their host stars, where tidal forces might drive extreme geological activity. Ganymede's magnetic field and layered ocean remain a puzzle waiting to be solved. Understanding the interaction between Ganymede's ocean and its rocky core could reveal whether it harbors hydrothermal activity, a potential driver for life. Future orbiters might use magnetic resonance imaging and radar to create detailed maps of Ganymede's subsurface, identifying areas where liquid water and energy sources converge. Callisto, with its ancient surface and isolated ocean, represents a different kind of mystery. Unlike Europa and Ganymede, Callisto experiences minimal tidal heating, raising questions about how its ocean has persisted. Missions could explore whether Callisto's ocean contains antifreeze compounds or other unique properties that allow it to remain liquid in such a cold environment. Callisto's low radiation levels and stable conditions also make it an excellent candidate for a human research outpost, potentially serving as humanity's first foothold in the outer solar system. Jupiter itself continues to captivate scientists as a model for gas giant behavior. While the Great Red Spot and its polar cyclones are focal points, the dynamics of the planet's deeper layers remain largely unknown. Theoretical models suggest that metallic hydrogen, a rare state of matter, exists under Jupiter's crushing pressures and might play a critical role in generating its magnetic field. Advanced probes capable of descending into Jupiter's atmosphere could confirm these theories, providing a clearer picture of how gas giants form and evolve. The auroras of Jupiter, fueled by its magnetic field and interactions with Io's volcanic activity, offer another opportunity for groundbreaking research. Observing these light shows in unprecedented detail could help scientists understand the role of magnetic fields in shaping planetary environments. Such insights are directly applicable to the study of exoplanets, where magnetic fields may protect atmospheres and influence habitability. Beyond the moons and the planet itself, Jupiter's Trojan asteroids, ancient remnants of the solar system's early days, are key to understanding how planets and moons formed. These bodies, sharing Jupiter's orbit, act as time capsules, preserving materials from the solar system's chaotic beginnings. Missions like Lucy will provide insights into their composition, adding pieces to the puzzle of planetary formation and migration. In the far future, the colonization of the Jovian system becomes a tantalizing prospect. A human base on Callisto could serve as a gateway for exploring the outer planets, enabling long-term missions to Saturn, Uranus, Neptune, and even interstellar space. Callisto's abundant water ice and stable conditions make it an ideal location for such an outpost. Innovations in radiation shielding, closed-loop life support systems, and in-situ resource utilization would be crucial to ensuring the success of these ventures. These advancements would not only support exploration, but also lay the groundwork for creating a sustainable human presence beyond Earth. Establishing infrastructure in the Jovian system could transform it into a hub for scientific research, technological development, and even economic activity, as humanity begins to harness the resources of the solar system. The exploration of Jupiter also forces us to confront deeper philosophical and ethical questions. If life exists elsewhere in the Jovian system, what responsibilities do we have to protect it? How do we ensure that our pursuit of knowledge does not harm the very environments we seek to understand? These questions challenge us to balance our drive to explore with a commitment to preserving the cosmic ecosystems we encounter. As we continue this journey, Jupiter serves as a source of inspiration for humanity. Its swirling storms, glowing auroras, and icy moons remind us of the universe's boundless creativity and complexity. The images and data returned from missions to the Jovian system captivate the public, inspiring future generations to pursue careers in science, engineering, and exploration. They remind us that the cosmos is not just a place of inquiry. It is a place of wonder, beauty, and connection. The legacy of Jupiter's exploration will endure as a testament to humanity's insatiable curiosity and determination. Every storm observed, every moon studied, and every question answered propels us closer to understanding the fabric of the universe. Jupiter and its moons call to us, urging us to push beyond the limits of what we know and embrace the challenges of the unknown. In the vast expanse of the cosmos, Jupiter is a beacon of discovery, a monument to the power of exploration, and a reminder of our place within the grand tapestry of the universe. The adventure is far from over. It is only just beginning. With each step forward, we move closer to unlocking the secrets of Jupiter and uncovering the truths that lie hidden among the stars. As the odyssey toward Jupiter and its mesmerizing moons continues, the possibilities for discovery and innovation expand, reflecting humanity's enduring quest to explore the unknown. Jupiter, a colossal giant of swirling storms and enigmatic forces, along with its dynamic moons, offers a tantalizing glimpse into the mechanics of the universe and the conditions that could foster life beyond Earth. The strategic exploration of Jupiter's moons. Future exploration will increasingly rely on multi-tiered mission architectures, combining orbiters, landers, and subsurface probes. Such missions are being designed to answer fundamental questions about the Jovian system's origins, evolution, and potential habitability. Europa, with its subsurface ocean beneath an icy crust, remains a high-priority target. Upcoming missions like Europa Clipper will pave the way for more ambitious follow-ups, including landers equipped with instruments capable of melting through the ice to access the hidden ocean below. These missions could incorporate nanobot swarms, tiny robots designed to explore the ocean autonomously, mapping underwater currents, sampling organic material, and searching for microbial or even multicellular life forms. On Ganymede, the largest moon in the solar system, the interplay between its magnetic field, layered ice, and suspected ocean raises questions about how energy flows within icy worlds. Advanced orbiters equipped with electromagnetic sensors could investigate how Ganymede's internal magnetic field interacts with Jupiter's powerful magnetosphere. Future landers could analyze surface features for evidence of past tectonic or cryovolcanic activity, revealing the moon's geological history. Io, with its unparalleled volcanic activity, presents unique challenges and opportunities. Observing Io's eruptions in real time requires orbiters capable of withstanding the moon's harsh environment. Heat-resistant landers or aerial drones could measure lava composition and thermal output, offering insights into the moon's interior and the tidal forces exerted by Jupiter and neighboring moons. Callisto, a moon marked by its ancient and heavily cratered surface, offers a stark contrast to the dynamic geology of Io and Europa. Missions here would focus on studying its chemical composition and investigating its subsurface ocean, potentially an isolated refuge of water and life-preserving conditions. Callisto's relative stability makes it a prime candidate for the establishment of human outposts, where astronauts could test technologies for living and working in deep space. The persistent mysteries of Jupiter itself. Jupiter's massive atmosphere remains a compelling mystery, with layers of gas and metallic hydrogen hiding clues about the planet's formation and evolution. Future missions could deploy atmospheric entry probes capable of surviving the intense pressure and temperature as they descend through the planet's thick cloud layers. These probes might analyze the transition from gaseous to metallic hydrogen, shedding light on the conditions that generate Jupiter's immense magnetic field. The Great Red Spot, a storm larger than Earth, continues to change and evolve, raising questions about its origins and longevity. High-resolution imaging and spectroscopy, coupled with long-term monitoring from orbiters, could provide unprecedented insights into the dynamics of this iconic feature. Understanding the physics behind the Great Red Spot might reveal new principles of atmospheric science applicable to gas giants throughout the galaxy. Expanding frontiers with advanced technology. To navigate Jupiter's extreme environment, innovative technologies will be essential. Radiation-hardened spacecraft equipped with AI-driven systems will allow for autonomous operations in high-radiation zones, such as the regions around Io and Europa. Nuclear-powered propulsion systems could reduce travel times and provide the energy needed for extended missions in the outer solar system. Cryobots capable of drilling through miles of ice will rely on cutting-edge materials science to withstand immense pressures and frigid temperatures. Submersibles operating beneath the ice will need advanced navigation systems and autonomous decision-making capabilities to adapt to unforeseen challenges. The deployment of solar sail-powered exploration craft offers another exciting avenue for outer solar system exploration. These lightweight, energy-efficient spacecraft could traverse vast distances, providing reconnaissance data to guide more focused missions. Human exploration of the Jovian system. While robotic missions will dominate the near future, the prospect of human exploration in the Jovian system is beginning to take shape. Callisto, with its low radiation levels and abundant resources, is the logical starting point for establishing a human presence. A research base on Callisto could serve as a hub for exploring Jupiter's other moons, allowing astronauts to control drones and rovers in real time. Living and working on Callisto would require innovations in habitat design, resource utilization, and life support systems. Water ice could be mined to provide drinking water, breathable oxygen, and hydrogen for fuel. Closed-loop life support systems would recycle waste, reducing the need for resupply from Earth. These technologies would not only enable sustainable living on Callisto, but also serve as testbeds for eventual missions to Mars, Saturn, and beyond. The ethical dimensions of exploration. As we expand our exploration of the Jovian system, we are confronted with profound ethical considerations. If microbial life is discovered on Europa or another moon, how will we ensure its protection? The potential to contaminate these environments with Earth-based microbes raises questions about the balance between exploration and preservation. Establishing guidelines for planetary protection will be essential, ensuring that our search for knowledge does not inadvertently destroy or alter alien ecosystems. These ethical considerations will demand a global framework, uniting nations and organizations in a shared commitment to responsible exploration. The broader implications for humanity. The study of Jupiter and its moons transcends planetary science, offering insights into the broader workings of the universe. Gas giants like Jupiter are among the most common types of planets discovered in other star systems, often with systems of moons that may be similar to our own. By understanding the Jovian system, we develop a framework for interpreting the data from distant exoplanetary systems. The search for life within Jupiter's icy moons also holds the promise of answering one of humanity's most profound questions. Are we alone in the universe? The discovery of even microbial life beyond Earth would suggest that life is a common phenomenon, potentially thriving in countless environments across the cosmos. Inspiring the next generation. The exploration of Jupiter ignites the imagination, inspiring people of all ages to dream about the possibilities of space exploration. Images of Europa's icy surface, Io's erupting volcanoes, and Jupiter's swirling storms captivate audiences worldwide, fostering a sense of connection to the cosmos. These missions remind us of the boundless potential of human ingenuity and the importance of pursuing knowledge for its own sake. The legacy of Jupiter's exploration. As humanity continues its journey into the Jovian system, we are not merely studying a distant planet and its moons. We are participating in a legacy of exploration that defines us as a species. Jupiter, with its grandeur and mystery, stands as a symbol of the infinite possibilities of the universe and humanity's unrelenting desire to explore, understand, and evolve. The discoveries awaiting us in the Jovian system will not only transform our understanding of the cosmos, but also shape the trajectory of human history. Jupiter calls to us, urging us to venture into the unknown, to push the limits of our capabilities, and to embrace the challenges of the infinite frontier. With each mission, each question answered, and each new mystery unveiled, we step closer to unraveling the ultimate truths of existence, guided by the wonders of this majestic gas giant and its remarkable family of moons. As humanity ventures further into the Jovian system, the journey becomes not just a scientific endeavor, but a defining chapter in our evolution as a spacefaring species. Jupiter, its swirling storms, and its family of extraordinary moons remind us of the boundless complexities of the universe and the potential for discovery that lies in the vast unknown. The next steps in exploring this celestial giant promise not only to deepen our knowledge, but to inspire a future where the stars are within our reach. The role of Jupiter in understanding exoplanetary systems. Jupiter is more than a planet. It is a keystone for interpreting the growing catalog of exoplanets. The majority of exoplanets discovered to date are gas giants, many in configurations vastly different from Jupiter's. While hot Jupiters orbit perilously close to their stars, many more are found at distances where icy moons could form and thrive. By studying Jupiter's influence on its moons, its magnetic field, and the interactions within its system, we refine our models of planetary formation and evolution, applying these lessons to distant solar systems. The detection of exomoons, moons orbiting exoplanets, is an emerging frontier in astronomy. Observations of Jupiter and its moons offer a natural laboratory to understand the potential for these far-off worlds to harbor oceans, volcanic activity, and even life. Could exomoons around gas giants in the habitable zones of other stars possess the same life-sustaining properties as Europa or Ganymede? Jupiter's system provides the groundwork to answer such questions. The next wave of exploration technology. Exploration of the Jovian system will require groundbreaking technologies designed to overcome the immense challenges posed by its harsh environment. Future missions will be equipped with innovations that are the direct descendants of today's pioneering spacecraft. Nuclear-powered exploration systems * with sunlight a mere fraction of its intensity at Jupiter's distance. Nuclear-powered spacecraft will play a critical role. These systems can generate electricity for decades, enabling long-term exploration of the Jovian system. AI-driven autonomous probes * as communication delays with Earth increase at Jupiter's distance. The need for probes capable of making decisions autonomously becomes paramount. These probes will navigate the rugged terrains of moons like Io and Europa, adapting to dynamic environments and ensuring the success of their missions. Cryobot and submersible combinations * missions to explore Europa's subsurface ocean will likely use a two-part system. A cryobot to melt through the icy crust, and a submersible to navigate the ocean below. These devices will carry instruments capable of detecting organic molecules, capturing imagery, and analyzing the chemical and thermal conditions of the alien sea. Radiation-hardened landers * the intense radiation belts around Jupiter present a formidable challenge for exploration. Future landers and orbiters will rely on advanced materials and shielding technologies to operate in these hostile environments, ensuring their longevity and data-gathering capabilities. Expanding human presence into the Jovian system. The dream of sending humans to Jupiter's moons is inching closer to reality. Callisto, with its relatively low radiation exposure and abundant water ice, remains the leading candidate for a human outpost. Establishing a base on Callisto would mark a monumental leap in space exploration, serving as a platform for studying Jupiter's system and testing technologies for long-duration missions to the outer solar system. A Callisto base could function as a hub for robotic exploration of nearby moons. Astronauts stationed there could remotely operate drones and rovers on Europa, Io, and Ganymede, conducting detailed studies without exposing themselves to the intense radiation around Jupiter. Such a base would also serve as a proving ground for technologies that will be critical for interplanetary colonization, including in situ resource utilization, ISRU extracting water from Callisto's ice and converting it into oxygen, drinking water, and hydrogen fuel. Advanced habitat design * creating radiation-shielded habitats capable of supporting humans for years at a time. Sustainable life support systems * implementing closed-loop systems that recycle air, water, and waste with high efficiency. The search for life, Europa, and beyond. The discovery of life in the Jovian system would be one of the most profound moments in human history. Europa remains the most likely candidate, with its vast subsurface ocean protected by an icy crust. However, the potential for habitability extends beyond Europa. Ganymede's larger ocean and its magnetic field offer another compelling possibility, as does Callisto's isolated, ancient ocean. Future missions will not only search for signs of life, but also explore the conditions necessary to sustain it. By studying the chemistry of these moons, including the presence of organic molecules and the availability of energy sources, scientists will refine their understanding of the factors that make a world habitable. Lessons for Earth and humanity. The study of Jupiter and its moons holds profound implications for understanding our own planet. Jupiter's weather systems, magnetic field, and gravitational influence provide insights into atmospheric dynamics, magnetic interactions, and planetary formation processes. By comparing Earth to its gas giant neighbor, scientists can better understand the forces that shaped our world and continue to influence it. Exploration of Jupiter also inspires reflection on humanity's place in the cosmos. The possibility of discovering life elsewhere forces us to confront fundamental questions about our uniqueness and our responsibilities as explorers. If microbial life exists on Europa or another moon, what ethical obligations do we have to protect it? How would such a discovery shape our understanding of life's resilience and its potential prevalence across the universe? Jupiter as a beacon for collaboration. The exploration of Jupiter has the power to unite humanity. Just as the Apollo program inspired a generation, a multinational effort to explore Jupiter and its moons could galvanize global collaboration. Joint missions combining the resources and expertise of space agencies worldwide would not only accelerate discoveries, but also demonstrate the strength of unity in pursuit of shared goals. The timeless call of Jupiter. Jupiter's majestic presence has inspired humanity for centuries, from ancient myths to modern science. As we delve deeper into its mysteries, the gas giant continues to captivate our imagination and challenge our ingenuity. Each mission, each discovery, and each step forward brings us closer to understanding this giant of the solar system and our place in the universe. The legacy of Jupiter's exploration will be one of boundless curiosity and relentless determination. It will remind us that in the face of immense challenges, humanity's greatest strength lies in its ability to dream, innovate, and explore. Jupiter, with its storms, moons, and secrets, calls to us, urging us to reach beyond our horizons and embrace the infinite possibilities of the cosmos. The journey has just begun. Jupiter awaits. Jupiter, with its boundless mysteries and profound influence, represents the essence of human curiosity and the pursuit of understanding. Every aspect of this planetary system invites deeper exploration, from its massive gravitational pull to the delicate interplay of forces shaping its moons. Each discovery builds upon centuries of scientific inquiry and pushes the boundaries of what we know about our solar system and the universe beyond. As missions to Jupiter evolve, the focus shifts toward integrating data from multiple perspectives, combining atmospheric studies, surface analyses, and subsurface exploration. Probes designed to withstand Jupiter's immense pressures and temperatures will dive deeper into its atmosphere, unraveling the secrets of its lower layers. These missions aim to answer critical questions about the planet's formation, including the origins of its metallic hydrogen layer and the processes that generate its immense magnetic field. These insights will not only deepen our understanding of gas giants, but also refine models of planetary formation that apply to exoplanetary systems. Jupiter's magnetic field, a structure so vast it extends beyond the orbit of Saturn, serves as both a shield and a sculptor within its system. Its interaction with charged particles creates auroras of breathtaking intensity at the poles, phenomena that provide clues about the dynamics of planetary magnetospheres. Observing how these magnetic interactions affect the planet's atmosphere and the orbits of its moons is critical to understanding similar processes on planets across the galaxy. Such studies could help determine whether magnetic fields are essential for maintaining atmospheres and fostering habitability on distant worlds. The moons of Jupiter continue to stand as some of the most compelling destinations for exploration in the solar system. Europa, with its subsurface ocean beneath an icy shell, remains the primary focus for the search for extraterrestrial life. Missions designed to sample Europa's surface or drill into its ocean are likely to deploy increasingly advanced robotic systems. These machines will carry instruments capable of analyzing water chemistry, detecting organic molecules, and assessing the energy sources available for potential life forms. The discovery of even the simplest microbes in Europa's ocean would fundamentally alter our understanding of the cosmos. suggesting that life can emerge and persist in environments vastly different from Earth's. Ganymede's layered structure and magnetic field offer another avenue for exploration, with its subsurface ocean providing a natural laboratory for studying the chemistry of icy worlds. Future missions will likely focus on mapping the Moon's internal structure and investigating the interactions between its ocean, rocky core, and icy crust. Understanding these dynamics could reveal how energy flows within such systems and whether they create environments capable of supporting life. Ganymede's magnetic field, the only one generated by a moon, adds another layer of intrigue, offering a chance to study how magnetic activity arises in icy bodies and what role it might play in shielding a moon's surface or ocean from cosmic radiation. Io, a volcanic wonderland unlike anything else in the solar system, challenges scientists to understand how extreme tidal heating can drive geological activity. Missions to Io will likely include high-resolution imaging systems and spectrometers designed to measure the composition of its volcanic plumes. Such missions aim to determine how Jupiter's immense gravity influences Io's interior, generating heat and driving eruptions that shape its constantly changing surface. These observations may also offer insights into the behavior of other volcanically active worlds, including rocky exoplanets experiencing similar tidal forces. Callisto, often regarded as the quiet sibling among Jupiter's Galilean moons, holds its own set of mysteries. With an ancient, heavily cratered surface and a suspected subsurface ocean, Callisto serves as a natural time capsule, preserving the history of the solar system's early days. Missions designed to study Callisto could investigate its ice and rock composition, providing clues about the primordial materials that formed the Jovian system. Callisto's stability and low radiation environment also make it an ideal candidate for a human research outpost, a stepping stone for long-term exploration of the outer solar system. The possibility of human presence in the Jovian system is no longer confined to the realm of imagination. With the development of advanced technologies for radiation shielding, resource extraction, and habitat sustainability, establishing a base on Callisto is becoming a tangible goal. Such a base would serve not only as a hub for robotic missions to explore the other moons, but also as a proving ground for technologies critical to human survival in deep space. Water ice from Callisto could be harvested to provide drinking water, breathable oxygen, and fuel, reducing dependence on Earth for resupply. The exploration of Jupiter is more than a journey to a distant world. It is a reflection of humanity's enduring spirit of discovery. Every mission, every observation, and every question answered brings us closer to understanding the forces that shaped our solar system and the potential for life beyond Earth. Jupiter's system, with its interplay of gravitational forces, magnetic fields, and geological activity, mirrors the complexity of the cosmos itself, providing a microcosm for studying the universal laws that govern planets and moons. As we look beyond Jupiter, the knowledge gained from studying its system will inform the exploration of exoplanetary systems, where gas giants and their moons are likely abundant. Understanding how Jupiter's moons interact with its gravity and magnetic field offers a blueprint for interpreting the behavior of similar systems light years away. By exploring the Jovian system, we prepare ourselves to recognize and understand environments that might host life in other star systems. The legacy of Jupiter's exploration will extend far beyond the data collected or the discoveries made. It will inspire future generations to dream boldly, to look beyond their immediate horizons, and to seek answers to the most profound questions about existence. Jupiter, with its boundless mysteries and cosmic grandeur, reminds us that the universe is vast and filled with possibilities, urging us to continue exploring, learning, and reaching for the stars. The exploration of Jupiter is a testament to humanity's resilience, ingenuity, and unyielding drive to understand the cosmos. Each mission, whether orbiting its tumultuous atmosphere or landing on one of its moons, builds upon centuries of curiosity and sets the stage for an era of unprecedented discovery. Jupiter and its complex system of moons offer not only scientific insights but also a philosophical perspective on our place in the universe. As we move deeper into the exploration of Europa, the potential for its subsurface ocean to host life remains a tantalizing possibility. The challenge lies in piercing its icy crust, which may be kilometers thick, and reaching the liquid ocean below. Advanced cryobots, equipped with heating elements and sensors, will be the tools to make this journey. These devices will be programmed to autonomously navigate the ice, analyzing its composition along the way, and deploying submersibles once the ocean is reached. These underwater explorers will search for organic compounds, thermal vents, and microbial life, indicators of a thriving, albeit hidden, ecosystem. Europa's plumes, ejecting water vapor and particles into space, provide another avenue for exploration. Flyby missions equipped with high-resolution spectrometers and particle analyzers can sample these plumes directly, offering a less invasive method of investigating the ocean's composition. By studying these plumes, scientists may detect biosignatures or identify the building blocks of life, such as amino acids and complex organic molecules, without the need to penetrate the ice. Ganymede's massive size and magnetic field continue to fascinate scientists. Future missions could deploy orbital platforms to map its magnetic interactions with Jupiter's magnetosphere, revealing how these forces influence the Moon's icy surface and subsurface ocean. The dynamics of Ganymede's magnetic field may also protect its interior environment, creating conditions more favorable for life. Landers on Ganymede could analyze its icy crust, searching for evidence of cryovolcanism or past liquid water flow, which could indicate geological activity that sustained habitability over billions of years. Io's volcanic landscape presents an entirely different set of scientific opportunities. The Moon's hyperactive geology, driven by tidal forces from Jupiter, makes it a living laboratory for understanding how intense gravitational interactions can shape a planet or moon. By deploying thermal mapping instruments and lava sampling landers, scientists could study Io's eruptions in detail, revealing how its interior remains so geologically active and what these processes suggest about early Earth and other volcanically active worlds. Callisto, often regarded as a tranquil counterpart to its more dynamic siblings, represents a unique opportunity to study a moon that has preserved its ancient surface largely untouched. Its craters hold records of impacts that stretch back to the solar system's formative years, offering a timeline of cosmic events. If Callisto's subsurface ocean is confirmed, it will add a surprising complexity to this seemingly static world, challenging assumptions about where water and life might persist. Callisto's stability and distance from Jupiter's intense radiation belts make it a prime candidate for future human missions, providing a relatively safe environment for long-term habitation. The planet Jupiter itself remains an inexhaustible source of scientific intrigue. Its atmosphere, with its alternating bands of jet streams, colossal storms, and the enigmatic Great Red Spot, is a model for studying atmospheric dynamics on a massive scale. Future atmospheric probes will delve deeper into its cloud layers, measuring temperature, pressure, and chemical composition, providing data to refine models of gas giant formation and evolution. These missions will seek to answer questions about Jupiter's core, whether it is solid or diffuse, and the mechanisms driving its extraordinary magnetic field. The auroras at Jupiter's poles, fueled by interactions between its magnetic field and charged particles from the solar wind and Io, are the most powerful in the solar system. Observing these auroras across multiple wavelengths will help scientists understand how magnetic fields shape planetary environments, including the potential for such fields to shield atmospheres and surface conditions from cosmic radiation. These insights have direct implications for the study of exoplanets, particularly those orbiting close to their host stars. Beyond the immediate exploration goals, Jupiter's system represents a training ground for technologies that will be essential for humanity's broader ambitions in space. Developing systems to operate in Jupiter's extreme radiation and low temperatures will pave the way for exploring other challenging environments, such as Saturn's moons Titan and Enceladus, or even exoplanets. Innovations in propulsion, resource extraction, and autonomous operations will ensure that the lessons learned from Jupiter extend far beyond its orbit. The exploration of Jupiter also invites us to reflect on the broader implications of our search. If life is found within the Jovian system, it will raise profound questions about life's universality and its adaptability. It will challenge us to consider what constitutes life, how it arises in diverse environments, and what ethical responsibilities we bear as explorers encountering new ecosystems. Jupiter's system, with its interplay of forces and extremes, is a microcosm of the universe's diversity and creativity. It reminds us that the cosmos is vast and filled with possibilities, urging us to approach the unknown with curiosity and reverence. As humanity reaches farther into space, Jupiter serves as a beacon of discovery and a testament to what is possible when we embrace our innate drive to explore. This journey is more than the pursuit of scientific knowledge. It is a celebration of human ingenuity, resilience, and imagination. Jupiter's storms, its radiant auroras, its active moons, and its enduring mysteries inspire us to dream beyond the confines of our planet. The exploration of Jupiter is not an endpoint, but a beginning, a step toward unraveling the secrets of the cosmos and understanding our place within it. The adventure continues, and with each new discovery, we come closer to grasping the infinite possibilities of the universe. As humanity continues its exploration of Jupiter, the layers of mystery surrounding this gas giant and its moons slowly peel away, revealing not just answers but new and profound questions. The Jovian system, with its swirling storms, immense gravitational pull, and vibrant collection of moons, stands as a celestial theater of extremes, offering a glimpse into the mechanisms that govern planetary systems throughout the galaxy. Jupiter's colossal magnetic field, a structure so vast that it dwarfs the Sun and its influence over charged particles, remains a cornerstone of ongoing research. The interactions between this magnetic field and the planet's moons create a dynamic environment unlike any other in the solar system. Io, for instance, continually injects material into Jupiter's magnetosphere through its volcanic activity, fueling radiation belts that are some of the most intense in the solar system. Understanding these interactions helps us grasp the role of magnetospheres in shaping planetary environments and influencing the evolution of atmospheres, not only here but also on distant exoplanets. The auroras at Jupiter's poles, the brightest in the solar system, are a direct manifestation of these magnetic interactions. Observing these auroras in greater detail across multiple wavelengths will allow scientists to map the flow of charged particles through Jupiter's magnetic field, revealing the mechanisms that produce such intense light displays. These studies will also enhance our understanding of how magnetic fields can shield or expose planets and moons to cosmic radiation, a factor critical to assessing the habitability of exoplanets. The search for life within Jupiter's moons remains one of the most compelling aspects of its exploration. Europa, with its ice-covered ocean, is at the forefront of this search. Future missions will likely focus on increasingly sophisticated technologies, such as miniature autonomous probes capable of descending through cracks in the ice to reach the ocean below. These probes will be designed to analyze the chemical composition of the water, searching for organic molecules, isotopic signatures, and potential metabolic byproducts indicative of biological activity. The icy shell of Europa itself may hold clues to the moon's habitability. Surface fractures, which expose material from the subsurface to the harsh environment of space, provide an opportunity to study the interaction between Europa's ocean and its surface. Spectral analysis of these regions could reveal the presence of salts, minerals, or organic compounds transported from the ocean below. Ganymede's vast subsurface ocean, coupled with its magnetic field, makes it a unique target for astrobiological and geophysical studies. Future missions could deploy orbiters to map the magnetic field's interaction with Jupiter's magnetosphere, helping scientists understand the protective role it might play in shielding the moon's interior from harmful radiation. Landers on Ganymede could drill into its icy crust to study the composition and layering of its surface, revealing how its internal ocean might interact with its rocky core. Callisto, often considered a relic of the early solar system, offers an entirely different perspective. Its heavily cratered surface and suspected subsurface ocean present a stark contrast to the geologically active worlds of Europa and Io. Callisto's ancient terrain may hold a record of the impacts and cosmic events that shaped the solar system's early history. Investigating its ice and rock composition could provide clues about the distribution of water and organic materials during the era of planet formation. Io, with its dramatic volcanic activity, presents a unique opportunity to study extreme geological processes. Future missions could employ high-resolution imaging and thermal mapping to observe its ever-changing surface. Understanding how Io's interior remains so active under the relentless tidal forces exerted by Jupiter and neighboring moons could shed light on similar processes occurring on rocky exoplanets subjected to intense gravitational interactions. Jupiter itself, the king of planets, continues to challenge our understanding of gas giants. Its atmosphere, with its towering storms, alternating jet streams, and enigmatic Great Red Spot, offers a natural laboratory for studying atmospheric dynamics on a massive scale. Probes designed to survive the intense pressures and temperatures of Jupiter's deeper layers could measure the composition and structure of the planet's atmosphere, shedding light on how such massive planets form and evolve. One of the most intriguing questions about Jupiter is the nature of its core. Is it solid, diffuse, or a mix of both? Understanding the structure of Jupiter's core will not only answer questions about its formation, but also refine models of gas giant evolution across the galaxy. These insights will be critical for interpreting the growing number of exoplanet discoveries, particularly those involving gas giants and their moons. The technological advancements required for exploring Jupiter will have far-reaching implications. Radiation-hardened electronics, autonomous systems, and efficient propulsion methods will enable not only more ambitious missions to the Jovian system, but also exploration of other outer planets and their moons. These technologies will also serve as a foundation for interstellar exploration, equipping humanity to push beyond the boundaries of our solar system. Human exploration of the Jovian system, while still a distant goal, is becoming increasingly plausible. Establishing a base on Callisto, the most radiation-safe of Jupiter's moons, would serve as a gateway for studying the entire Jovian system. Such a base could support robotic exploration of Europa, Ganymede, and Io, while also testing technologies for long-term survival in deep space. The presence of water ice on Callisto provides a critical resource for sustaining human life, offering a potential source of drinking water, oxygen, and hydrogen fuel. The exploration of Jupiter and its moons also raises profound philosophical and ethical questions. If microbial life is discovered, how should humanity proceed? What responsibilities do we have to protect these alien ecosystems? And how do we balance our desire for knowledge with the need for preservation? These questions force us to confront the broader implications of our actions as explorers and stewards of the universe. Jupiter's system is more than a collection of fascinating worlds. It is a microcosm of the forces that shape planetary systems throughout the galaxy. The interplay of gravity, magnetism, geology, and chemistry within the Jovian system mirrors processes occurring on distant exoplanets and their moons. By studying Jupiter, we are not just unlocking the secrets of our solar system. We are laying the groundwork for understanding the nature of planetary systems across the cosmos. The legacy of Jupiter's exploration will be one of inspiration, unity, and boundless curiosity. It reminds us that the universe is vast, filled with wonders waiting to be discovered. As we continue to venture into the unknown, Jupiter stands as a beacon, urging us to dream bigger, explore further, and embrace the infinite possibilities of the cosmos. The journey to understand Jupiter and its moons is far from over. It is a journey that will shape the future of humanity and our place in the universe. The journey to uncover the mysteries of Jupiter and its moons is an endeavor that transcends the limits of science and technology. It is a testament to humanity's enduring curiosity and a reflection of our innate desire to push boundaries and explore the unknown. Each step forward in this exploration brings with it not only profound discoveries, but also a greater understanding of the forces that shape the universe and our place within it. As robotic missions advance, the ability to interact with the Jovian system at unprecedented depths and scales is becoming a reality. Future exploration of Jupiter's Great Red Spot will likely involve specialized atmospheric probes capable of descending deep into the storm's swirling layers. These probes will measure the pressure, temperature, and chemical composition of the gases within, unraveling the dynamics that sustain this colossal tempest. Understanding why the Great Red Spot has persisted for centuries and what is causing its gradual shrinking could reveal new insights into the behavior of storms on planetary scales, with implications for understanding weather systems on other gas giants and even exoplanets. The polar regions of Jupiter are equally compelling, with their intricate patterns of cyclones and anticyclones. Observations from the Juno spacecraft have already provided striking imagery of these features, but future missions could focus on long-term monitoring to understand how they form, interact, and evolve. These studies may also shed light on the fundamental processes governing fluid dynamics in rapidly rotating planets, deepening our knowledge of atmospheric behavior across the solar system. Jupiter's immense magnetosphere, a structure so vast it could hold all the other planets within its bounds, continues to be a major focus of scientific inquiry. Future missions equipped with highly sensitive magnetometers and particle detectors will map the structure of this magnetic field in greater detail, revealing how it interacts with the solar wind, charged particles from Io, and the plasma torus that encircles the planet. These interactions create phenomena such as intense radiation belts and the brightest auroras in the solar system. By studying these processes, scientists can better understand the protective and destructive roles of magnetic fields, both in our solar system and in distant planetary systems. The moons of Jupiter remain unparalleled in their scientific allure, each offering a unique perspective on planetary processes and the potential for life. Europa's ocean, hidden beneath a thick shell of ice, continues to be a prime candidate in the search for extraterrestrial life. Advances in technology may soon enable missions to deploy underwater autonomous vehicles capable of exploring this vast alien sea. These vehicles could map the ocean floor, search for hydrothermal vents, and analyze water chemistry, providing the clearest picture yet of Europa's potential habitability. In tandem with ocean exploration, Europa's icy surface will remain a critical area of study. The cracks, ridges, and chaos terrains that characterize the moon's surface offer a window into the dynamic interactions between the ocean below and the icy crust above. By analyzing surface deposits ejected by plumes or brought up through cracks, missions could determine whether organic molecules or signs of biological activity exist within Europa's ocean. Ganymede, with its magnetic field and layered interior, presents a different but equally compelling target. Its massive size and the presence of both a rocky core and a subsurface ocean make it a natural laboratory for studying the evolution of icy worlds. Missions to Ganymede could deploy seismic instruments to detect tectonic activity and measure the thickness of its ice shell. Such studies might reveal whether Ganymede's ocean interacts with its rocky core, a key factor in determining its potential for supporting life. Callisto's ancient and heavily cratered surface continues to intrigue scientists as a time capsule of the early solar system. If its suspected subsurface ocean exists, it would provide a fascinating counterpoint to the more dynamic oceans of Europa and Ganymede. Missions to Callisto could focus on analyzing its ice and rock composition, determining how its ocean has remained stable in an environment with minimal tidal heating. Callisto's relative calm and low radiation levels also make it an attractive candidate for a future human outpost, where astronauts could conduct research and serve as operators for robotic missions exploring other Jovian moons. Io's intense volcanic activity offers an unparalleled opportunity to study geological processes on a moon subjected to extreme tidal forces. Future missions to Io could deploy heat-resistant landers to monitor its volcanic eruptions in real time, providing data on the composition and behavior of its lava flows. These observations would not only enhance our understanding of Io's interior, but also offer insights into how similar tidal forces might influence geological activity on exoplanets or other moons. Jupiter itself, as the largest and most massive planet in our solar system, remains a critical piece of the puzzle in understanding planetary formation and evolution. Its gravity and composition reflect the conditions of the early solar system, making it a natural laboratory for studying how planets form and migrate. By analyzing Jupiter's deep atmosphere and core, scientists can refine models of gas giant formation, shedding light on the processes that created the diverse array of planets now being discovered around other stars. The exploration of Jupiter also has profound implications for humanity's future in space. The technological advancements required to navigate its intense radiation, vast distances, and extreme conditions will drive innovation that extends beyond planetary science. These technologies will be critical for exploring other outer solar system destinations, such as Saturn's moons Titan and Enceladus, and for preparing for interstellar exploration. The possibility of establishing a human presence in the Jovian system is no longer the realm of science fiction. Callisto, with its abundant water ice and low radiation exposure, could serve as a stepping stone for humanity's expansion into the outer solar system. A base on Callisto would allow for real-time control of robotic missions to Europa, Io, and Ganymede, enabling more efficient exploration of these moons. It would also provide a platform for testing life support systems, resource utilization technologies, and habitat designs necessary for longer missions to Saturn and beyond. As humanity continues to explore Jupiter, the lessons learned will resonate far beyond the scientific community. Jupiter's system offers a vision of what is possible when curiosity, ingenuity, and collaboration drive exploration. It challenges us to think not only about the mechanics of the cosmos, but also about our responsibilities as explorers. How will we ensure that our search for knowledge does not harm the environments we study? What ethical frameworks will guide us if we encounter life beyond Earth? Jupiter stands as a symbol of the universe's infinite complexity and beauty, a reminder that the answers we seek often lead to deeper questions. Its storms, moons, and magnetic fields are more than just scientific phenomena. They are a call to action, urging humanity to look beyond its immediate horizons and embrace the vast unknown. The journey to understand Jupiter is a journey to understand ourselves and our place in the cosmos. As we continue this voyage, we are reminded that exploration is not just about reaching a destination. It is about the process of discovery, the challenges overcome, and the new perspectives gained. Jupiter awaits, a beacon of wonder and possibility, guiding us toward a future where the stars are within our reach and the universe becomes a little more familiar with every step we take. As humanity deepens its exploration of Jupiter, the layers of understanding peel back to reveal a universe far more intricate and interconnected than we ever imagined. Each discovery within the Jovian system not only sheds light on the mechanisms governing our solar system, but also hints at universal processes that may shape countless other planetary systems across the galaxy. Jupiter's role as a gravitational architect continues to captivate scientists. Its immense gravity acts as both a protector and a disruptor within the solar system, influencing the orbits of asteroids, comets, and even the inner planets. By studying the intricate dance of objects within Jupiter's gravitational field, such as its Trojan asteroids, scientists gain insights into the chaotic early days of the solar system. These asteroids, locked in stable points along Jupiter's orbit, are time capsules preserving the raw materials from which planets formed. Missions like Lucy are set to uncover their composition and structure, offering a glimpse into the primordial building blocks of planetary formation. Jupiter's gravity also sculpts the dynamics of its moons, creating a complex web of tidal forces that shape their geology and atmospheres. The Laplace resonance between Io, Europa, and Ganymede, where their orbital periods align in a precise ratio, illustrates the power of these gravitational interactions. This resonance not only drives Io's volcanic activity, but also generates heat within Europa and Ganymede, sustaining their subsurface oceans. By analyzing these interactions, scientists can refine their understanding of tidal heating, a phenomenon that may sustain liquid water on exoplanetary moons and distant star systems. The exploration of Europa's ocean remains a pinnacle of astrobiological research. Beneath its icy crust lies a body of water that may contain twice the volume of Earth's oceans, warmed by tidal forces and potentially interacting with the moon's rocky core. These conditions are strikingly similar to those found at Earth's hydrothermal vents, where life thrives in the absence of sunlight. If similar ecosystems exist on Europa, they could represent not only an independent origin of life, but also a model for how life might arise in other parts of the cosmos. To explore Europa's hidden ocean, future missions will employ technologies capable of reaching unprecedented depths. Cryobots, designed to penetrate the ice, will carry sensors to detect chemical gradients, temperature variations, and salinity levels as they descend. Upon reaching the ocean, these robots will deploy submersibles equipped with cameras and spectrometers to explore the water column and ocean floor. Such missions will require precision engineering to overcome the challenges of extreme pressure, low temperatures, and the need for autonomous operation in an environment unreachable by direct communication with Earth. Ganymede's ocean, though buried beneath a much thicker layer of ice, presents another tantalizing target. The Moon's layered structure suggests that its ocean may be sandwiched between layers of ice, potentially isolating it from the rocky core below. Understanding how such an ocean remains liquid and whether it exchanges materials with the core is crucial to assessing its habitability. Future missions could deploy seismic instruments to measure ice movement or study magnetic field variations to infer the depth and salinity of its ocean. Io, the most geologically active body in the solar system, offers a contrasting perspective on how tidal forces shape a moon's evolution. Its constant volcanic eruptions, driven by Jupiter's gravitational pull, provide a natural laboratory for studying extreme geological processes. Missions to Io could monitor its surface in real time, capturing the dynamics of lava flows, plume ejections, and surface reshaping. These studies not only enhance our understanding of Io, but also offer insights into how volcanic activity might influence atmospheres and climates on exoplanets. Callisto's ancient surface, marked by craters and a suspected subsurface ocean, serves as a bridge between the past and present of the solar system. Its relative stability and low radiation environment make it an excellent candidate for long-term human exploration. A base on Callisto could provide a safe haven for astronauts, enabling detailed studies of Jupiter's system while testing technologies for deeper space missions. Such a base would also allow for real-time operation of robotic explorers on Europa, Io, and Ganymede, maximizing scientific returns without risking human exposure to radiation. Jupiter itself continues to pose questions about the formation and behavior of gas giants. The planet's atmosphere, a turbulent mix of hydrogen, helium, and trace compounds, offers a window into processes that shape planetary atmospheres on a massive scale. By studying the depth and dynamics of its jet streams, the structure of its storms, and the behavior of its deep interior, scientists can develop models applicable to gas giants across the universe. The mysteries of Jupiter's core remain a central focus. Whether the core is solid, diffuse, or partially dissolved holds significant implications for understanding how gas giants form. Probes capable of measuring gravitational variations and analyzing the planet's magnetic field could provide critical data to resolve this debate. These insights will inform our understanding of the conditions necessary for the formation of planets like Jupiter and their role in shaping planetary systems. Technological advancements will continue to drive the exploration of Jupiter and its moons. Nuclear-powered spacecraft, capable of sustained operations in the outer solar system, will enable longer and more ambitious missions. Autonomous systems, equipped with advanced AI, will navigate the challenges of radiation, extreme temperatures, and communication delays, ensuring the success of missions in the Jovian system's harsh environments. The potential for human exploration of Jupiter's moons represents a bold frontier. Establishing a base on Callisto, with its abundant water ice and relative safety from radiation, would be a transformative step in humanity's expansion into the outer solar system. Such a base could serve as a hub for scientific research, resource extraction, and even as a launch point for missions to Saturn and beyond. Water ice could be converted into drinking water, oxygen, and hydrogen fuel, supporting long-term human presence and reducing reliance on resupply from Earth. As we push further into the Jovian system, the ethical dimensions of exploration become increasingly important. If life is discovered, whether on Europa, Ganymede, or another moon, humanity will face profound questions about its responsibilities as explorers. How do we balance our desire for knowledge with the need to protect alien ecosystems? What measures will we take to ensure that our activities do not irreversibly alter these pristine environments? These considerations will shape the policies and principles that guide future exploration efforts. Jupiter and its moons serve as a reminder of the universe's boundless possibilities and the complexity of the forces that shape it. They challenge us to think creatively, to act boldly, and to pursue discovery with humility and purpose. The Jovian system is not just a destination for exploration. It is a gateway to understanding the cosmos and humanity's place within it. As we continue this journey, we are reminded that the exploration of Jupiter is not simply about unlocking its secrets. It is about the process of discovery itself. It is about embracing the unknown, pushing the limits of what is possible, and inspiring future generations to dream even bigger. Jupiter awaits, a beacon of curiosity and a testament to the infinite potential of human exploration. Jupiter, the king of planets, stands as a symbol of grandeur and mystery in our solar system. Its colossal size, powerful storms, and captivating moons make it one of the most fascinating celestial objects for scientists and stargazers alike. But what truly makes Jupiter extraordinary lies beneath its swirling clouds and orbiting entourage, a story as vast as the gas giant itself. Jupiter is so massive that it contains more than twice the combined mass of all the other planets in our solar system. If it were about 80 times more massive, it could have become a star, illuminating the darkness of space. This enormous size has earned it a reputation as a vacuum cleaner of the solar system, pulling in comets and asteroids that might otherwise threaten the inner planets. Its gravitational influence acts as a shield, yet sometimes redirects dangerous objects toward Earth, a cosmic irony that highlights Jupiter's dual role as protector and potential threat. The planet's atmosphere is a spectacle of chaos and beauty. Dominated by hydrogen and helium, Jupiter's skies are painted with ammonia clouds, creating vibrant bands of white, orange, and red. These bands, separated by jet streams moving at different speeds, form a mesmerizing pattern that can be seen from telescopes on Earth. Among these features lies the Great Red Spot, a storm larger than Earth that has raged for centuries. Recent observations suggest that the storm is shrinking, but its ferocity remains unmatched. Scientists are still deciphering why this iconic tempest is gradually fading, but its legacy as a natural wonder persists. Beneath the clouds, the mysteries deepen. Jupiter lacks a solid surface, transitioning instead into a dense liquid hydrogen sea as you dive deeper into its atmosphere. At extreme pressures, this liquid hydrogen transforms into metallic hydrogen, a rare state of matter where hydrogen behaves like a metal, conducting electricity and creating Jupiter's immense magnetic field. This magnetic field, the largest in the solar system, extends millions of miles into space, trapping charged particles and creating intense radiation belts that would be lethal to any spacecraft or human that ventured too close. Yet, as remarkable as Jupiter itself is, its moons add an entirely new dimension to its allure. With at least 95 confirmed moons and counting, Jupiter's satellite system is like a miniature solar system. Among these, 4 moons stand out: Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons. Each one offers a unique glimpse into the diversity of celestial phenomena. Io, the closest Galilean moon to Jupiter, is the most volcanically active body in the solar system. Its surface is a kaleidoscope of yellows, reds, and oranges, created by continuous volcanic eruptions. These eruptions are fueled by tidal heating, a process where Jupiter's immense gravity flexes Io, generating internal friction and heat. The sheer intensity of volcanic activity reshapes Io's surface in real time, making it an ever-changing world of fire and brimstone. Europa, the second Galilean moon, is a stark contrast to Io's fiery landscape. Europa's surface is a smooth shell of ice, crisscrossed with cracks and ridges. Beneath this icy crust lies a hidden ocean, kept liquid by the same tidal heating that fuels Io's volcanoes. This subsurface ocean, potentially holding more water than all of Earth's oceans combined, is a prime candidate in the search for extraterrestrial life. The discovery of water plumes erupting from Europa's surface has excited scientists, suggesting that sampling this ocean might be within reach of future missions. Ganymede, the largest moon in the solar system, is a giant in its own right. Bigger than Mercury, Ganymede boasts its own magnetic field, a rarity for a moon. Its icy surface is a mix of ancient, cratered regions and younger, grooved terrains that hint at past geological activity. Some scientists speculate that a salty ocean might exist beneath Ganymede's surface, further amplifying its intrigue as a potential harbor for life. Callisto, the outermost of the Galilean moons, offers a glimpse into the ancient past of the solar system. Its heavily cratered surface has remained largely unchanged for billions of years, acting as a time capsule for planetary formation. While Callisto lacks the internal activity of its siblings, its stability and low radiation environment make it an attractive target for future human exploration and possibly even colonization. Jupiter's influence extends beyond its moons. The planet is surrounded by a faint ring system, composed mainly of dust particles from its smaller moons. Unlike the bright, icy rings of Saturn, Jupiter's rings are subtle and difficult to observe, a hidden gem in the gas giant's vast domain. As we continue to explore Jupiter and its moons, our understanding of the solar system's complexity deepens. NASA's Juno spacecraft has provided unprecedented insights into Jupiter's atmosphere, magnetic field, and interior structure. Future missions, such as the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, aim to unlock the secrets of the Galilean moons, bringing us closer to answering profound questions about the origins of our solar system and the possibility of life beyond Earth. Jupiter's story is a testament to the wonders of the cosmos, a reminder that even in the vastness of space, beauty and mystery are intertwined. Its grandeur invites us to look up, to dream, and to push the boundaries of exploration as we seek to understand our place in the universe. The King of Planets continues to reign, not just as a celestial giant, but as a symbol of the boundless curiosity that defines humanity. The marvels of Jupiter do not end with its sheer size, swirling storms, or enigmatic moons. It is also a dynamic laboratory for understanding the forces that shape planetary systems, a key to unlocking secrets about the early days of our solar system. Jupiter's gravitational might has sculpted the orbits of countless celestial bodies, serving as a stabilizing force that has likely influenced the evolution of life on Earth. But beyond this protective role, Jupiter's relationship with its moons and its complex magnetosphere reveals a symphony of celestial interactions that continue to astonish astronomers. One of the most intriguing aspects of Jupiter's magnetosphere is its interaction with Io, whose volcanic activity releases vast amounts of sulfur and oxygen into space. These elements form a plasma torus, a glowing donut-shaped cloud that encircles Jupiter. As Io orbits within this torus, its volcanic emissions are stripped by Jupiter's magnetic field, creating massive electrical currents that flow between the Moon and the planet. These currents generate intense auroras, far more powerful than Earth's northern and southern lights. The spectacle of Jupiter's auroras, glowing in ultraviolet wavelengths, is a vivid reminder of the immense energy at play in this system. Europa, too, contributes to this magnetic dance. The Moon's hidden ocean, combined with its thin, salty ice crust, creates a conductive layer that interacts with Jupiter's magnetic field. This interaction induces secondary magnetic fields, offering indirect but compelling evidence of the vast ocean below. Scientists believe that the shifting of these fields could provide critical insights into the ocean's composition and its potential to support life. These discoveries fuel ongoing efforts to design probes capable of landing on Europa's surface, or even penetrating its icy crust to explore the alien waters beneath. Ganymede's magnetic field adds yet another layer of complexity. As the only moon in the solar system with a magnetic field, Ganymede produces auroras of its own, interacting with Jupiter's massive magnetosphere in a celestial tug-of-war. These interactions could reveal more about the moon's internal structure, including the suspected ocean beneath its icy shell. With instruments capable of analyzing these magnetic fluctuations, upcoming missions aim to uncover whether Ganymede could support microbial life, or if its subsurface ocean is simply a relic of a more dynamic past. While Callisto might seem less active in comparison, its undisturbed surface and potential underground ocean suggest it may hold secrets just as profound. Callisto's distance from Jupiter places it outside the worst of the planet's intense radiation, making it an appealing destination for human exploration. Some scientists even envision Callisto as a stepping stone for missions venturing further into the outer solar system. Its ancient surface could provide valuable clues about the bombardment history of the early solar system, shedding light on how planets and moons have evolved over billions of years. Jupiter's gravitational dominance doesn't just affect its moons. The planet plays a crucial role in shaping the asteroid belt, the collection of rocky and metallic bodies orbiting the Sun between Mars and Jupiter. Jupiter's gravity perturbs these asteroids, preventing them from coalescing into a planet. These disruptions create gaps in the belt, known as Kirkwood gaps, and occasionally eject asteroids into trajectories that bring them closer to the inner planets. This constant gravitational interplay highlights Jupiter's profound influence across the solar system. Even comets are not immune to Jupiter's pull. Some, like comet Shoemaker-Levy 9, have been captured by Jupiter's gravity, leading to dramatic collisions with the gas giant. When Shoemaker-Levy 9 struck Jupiter in 1994, it left scars on the planet's atmosphere that were visible for months. These collisions provide a rare opportunity to study the composition of Jupiter's atmosphere and the mechanics of such cosmic impacts. At the same time, they underscore the importance of Jupiter as a cosmic shield, reducing the number of comets that could potentially strike Earth. The study of Jupiter continues to inspire, revealing not just answers, but new questions that challenge our understanding of planetary systems. For instance, what lies at the core of this gas giant? Theories suggest a dense, rocky core surrounded by layers of metallic hydrogen, but direct evidence remains elusive. Juno's gravity measurements are helping to refine these models, offering tantalizing hints about Jupiter's deep interior and the processes that led to its formation. And what of its atmosphere? The alternating bands of clouds, driven by powerful jet streams, hint at a complex interplay between heat, rotation, and chemical composition. Lightning storms larger than any seen on Earth illuminate the planet's deep atmosphere, a reminder of the raw energy that powers this giant world. By studying these phenomena, scientists hope to draw parallels to the weather systems of other planets, including Earth, improving our understanding of atmospheric dynamics across the cosmos. The exploration of Jupiter is far from over. Future missions will not only study its moons, but also explore its faint rings, its lesser-known outer satellites, and its place in the broader context of exoplanetary systems. Jupiter serves as a benchmark for understanding gas giants and other star systems, many of which are hot Jupiters that orbit perilously close to their stars. By comparing these alien worlds to our own Jupiter, scientists can unravel the diversity of planetary systems and refine theories about planet formation. Jupiter remains an emblem of the infinite possibilities that space holds. Its turbulent atmosphere, complex magnetic field, and intriguing moons are reminders of the universe's boundless creativity. As we continue to probe its secrets, we are not just exploring a distant planet, but also delving into the story of how our own world came to be. Every discovery about Jupiter brings us closer to understanding the cosmos, reminding us that even the most familiar objects in the night sky can surprise us in ways we never imagined. As humanity's gaze remains fixed on Jupiter, the ongoing discoveries surrounding this gas giant reinforce its role as both a cornerstone of our solar system and a gateway to understanding the broader universe. The profound interplay of forces shaping Jupiter, from its gravity to its magnetic field, reflects not just the power of nature, but also the intricate balance that governs celestial mechanics. But what lies ahead in our exploration of Jupiter? The next steps promise to be nothing short of revolutionary. One of the most highly anticipated missions to Jupiter is NASA's Europa Clipper, slated to launch in the coming years. This spacecraft will focus on the moon Europa, with its hidden ocean that has captivated the imagination of scientists and dreamers alike. Equipped with advanced instruments, Europa Clipper will scan the icy surface for signs of habitability, analyze the water vapor plumes detected by previous missions, and map the moon's crust in detail. These efforts are aimed at uncovering whether Europa's subsurface ocean could support life, making it one of the most compelling endeavors in the search for extraterrestrial life. Simultaneously, the European Space Agency, ESA, is preparing the Jupiter Icy Moons Explorer JUICE mission, which will explore not only Europa, but also Ganymede and Callisto. JUICE will perform multiple flybys of these moons before eventually entering orbit around Ganymede, making it the first spacecraft to orbit a moon other than our own. Its instruments will delve into the geology, subsurface oceans, and potential magnetic interactions of these moons, deepening our understanding of their evolution and habitability. The questions these missions aim to answer extend far beyond the confines of our solar system. By studying Jupiter's moons, we can better understand the potential for life in other planetary systems. For instance, Could exomoons orbiting gas giants and other star systems also harbor oceans beneath icy shells? The lessons learned from Europa, Ganymede, and Callisto could provide a template for identifying habitable worlds elsewhere in the cosmos. Yet, even as we focus on the moons, Jupiter itself remains an enigma. Recent data from NASA's Juno mission, which has been orbiting Jupiter since 2016, has already revolutionized our understanding of the planet. Juno's detailed observations of Jupiter's polar regions revealed striking geometric arrangements of cyclones, forming massive, persistent weather patterns unlike anything on Earth. These discoveries challenge existing models of atmospheric dynamics, offering fresh insights into the forces shaping gas giants. Juno has also uncovered new details about Jupiter's magnetic field, revealing that it is far more uneven and dynamic than previously thought. This asymmetry suggests that processes deep within Jupiter's core are more complex than scientists imagined. Understanding these magnetic phenomena could shed light on the formation of other gas giants, both in our solar system and beyond. Despite these advancements, Jupiter's core remains one of the greatest mysteries. Juno's measurements of the planet's gravitational field suggest that its core might not be a well-defined, solid structure, but rather a diffuse region of heavy elements mixed with hydrogen and helium. This so-called fuzzy core hypothesis raises questions about how Jupiter formed. Did it grow from the accretion of solid material before capturing its thick atmosphere? Or did it form directly from a collapsing gas cloud? The answers to these questions are crucial for piecing together the puzzle of planetary formation. Looking further into the future, concepts for even more ambitious missions to Jupiter are taking shape. Scientists have proposed sending robotic submarines to explore the oceans of Europa and Ganymede, or deploying drones to soar through Jupiter's atmosphere, sampling its chemical makeup and studying its winds up close. Such missions, while still in the conceptual phase, hint at the boundless potential of exploring this gas giant and its moons. Jupiter's exploration also holds profound implications for humanity's broader journey into space. The lessons learned from surviving and thriving in the harsh environment near Jupiter, where radiation levels are extreme and communication delays with Earth can stretch to over an hour, will inform the technologies and strategies needed for future deep space missions. The challenges of navigating Jupiter's intense radiation belts, for example, have already pushed engineers to design spacecraft with unprecedented levels of shielding, innovations that could benefit future missions to other planets and moons. Furthermore, Jupiter's role as a cosmic shield for Earth continues to underscore its importance in the context of planetary defense. By studying how Jupiter deflects or captures potentially hazardous asteroids and comets, scientists can refine models for protecting Earth from similar threats. In this sense, Jupiter's influence extends beyond its immediate vicinity, playing a vital role in the long-term survival of life on our planet. But perhaps the most profound impact of exploring Jupiter is the way it reshapes our perspective on the universe. Every discovery about this planet and its moons adds to the narrative of cosmic wonder, reminding us of the infinite diversity and complexity of the cosmos. Whether it's the breathtaking storms of the Great Red Spot, the volcanic fury of Io, the icy mysteries of Europa, or the ancient surface of Callisto, Jupiter's system invites us to contemplate questions that transcend the boundaries of science. What does it mean to be part of a universe so vast and varied? How do the forces that shape Jupiter relate to the forces that shape our own lives? And, perhaps most intriguingly, are we truly alone in this cosmic expanse? Or do the oceans of Europa or the hidden layers of Ganymede harbor life waiting to be discovered? Jupiter stands as a beacon in the night sky, a constant reminder of the grandeur of the cosmos and the unending pursuit of knowledge that defines us as a species. Its wonders compel us to keep looking up, to keep exploring, and to embrace the mysteries that lie beyond. In doing so, we not only uncover the secrets of a distant world, but also deepen our connection to the universe and our place within it. As we push the boundaries of exploration, Jupiter remains a focal point for the convergence of cutting-edge technology and human ingenuity. The planet's secrets are not just scientific puzzles, but also opportunities to advance our understanding of physics, chemistry, and biology. Each discovery paves the way for new questions, proving that exploration is an iterative process, constantly evolving with each mission, observation, and breakthrough. The search for life, one of the most profound quests in science, finds a unique stage around Jupiter. Europa's subsurface ocean, protected from the radiation-bombarded surface by an icy crust, represents a prime candidate for harboring life. Astrobiologists are particularly interested in whether hydrothermal vents might exist on the ocean floor, similar to those found on Earth, where life thrives in complete darkness, powered by chemical reactions rather than sunlight. If such ecosystems exist on Europa, it would revolutionize our understanding of what is required for life and suggest that life might be far more common in the universe than previously thought. But the implications don't stop at Europa. Ganymede, with its own potential ocean beneath a thick layer of ice, offers a different environment where life could emerge or be sustained. The possibility of multiple moons within a single planetary system having the conditions for life challenges the notion that Earth is uniquely positioned in the cosmos. It hints at a universe where life might arise in diverse and unexpected forms, shaped by the unique environments of alien worlds. The technological challenges of exploring Jupiter and its moons are immense, yet they also drive innovation in space exploration. Missions to Jupiter must endure its intense radiation, which requires advanced shielding to protect sensitive instruments. Solar-powered spacecraft like Juno demonstrate how technology has evolved to operate efficiently even in the dim light of the outer solar system. Future missions will likely incorporate artificial intelligence, enabling probes to make decisions autonomously as they explore environments where real-time communication with Earth is impractical. In addition to robotic missions, the idea of human exploration of Jupiter's system has captured imaginations. While the planet itself is inhospitable, its moons could serve as bases for future exploration. Callisto, with its low radiation levels and stable environment, is often cited as a potential site for a human outpost. Such an endeavor would require advancements in life support systems, radiation protection, and propulsion technologies, but the rewards would be monumental: a permanent human presence in the outer solar system and a new frontier for discovery. Jupiter also serves as a model for understanding exoplanets, particularly gas giants orbiting other stars. Many of these exoplanets, known as hot Jupiters, orbit very close to their stars, experiencing extreme temperatures and conditions unlike anything in our solar system. By studying Jupiter in detail, we gain a reference point for interpreting the data we collect about these distant worlds. The dynamics of Jupiter's atmosphere, its magnetic field, and its interactions with its moons all contribute to the broader field of comparative planetology, helping us to understand the diversity of planetary systems. The lessons learned from Jupiter's moons could also inform the search for exomoons, natural satellites orbiting exoplanets. These exomoons might be as diverse as the Galilean moons, with some potentially hosting conditions favorable to life. As telescopes and detection methods improve, finding and studying these distant moons may become a reality, further expanding our understanding of where life might exist in the universe. The cultural and philosophical impact of exploring Jupiter cannot be overstated. For millennia, Jupiter has been a symbol of power and mystery in human mythology and astronomy. Today, it represents a bridge between the known and the unknown, a tangible reminder of how far humanity has come in its quest to understand the cosmos. The more we learn about Jupiter, the more it inspires us to continue exploring, to ask bigger questions, and to embrace the unknown with curiosity and determination. As we stand at the threshold of new discoveries, Jupiter beckons us with its grandeur, urging us to reach further than ever before. The journey to understand this giant world and its enigmatic moons is not just about science. It's a testament to the human spirit, the drive to explore, and the unyielding desire to uncover the secrets of the universe. In the shadow of Jupiter, we find not just answers but also the courage to keep searching, knowing that the next revelation is always just beyond the horizon. Jupiter's ongoing exploration represents a remarkable intersection of human curiosity and the boundless complexity of the cosmos. Every new mission, observation, and theory uncovers deeper layers of understanding, revealing that the King of Planets is not merely a scientific wonder, but a dynamic laboratory for understanding the universe itself. Its immense scale, diversity, and influence continue to challenge the limits of what we know and inspire new generations of explorers, engineers, and dreamers. The magnetic field of Jupiter is a prime example of the profound mysteries still left to unravel. Stretching millions of miles into space, this invisible force field creates a vast and dynamic environment teeming with energy and charged particles. The auroras at Jupiter's poles, glowing in ultraviolet and infrared light, are direct manifestations of this powerful magnetosphere, providing a stunning visual testament to the forces at play. The study of these auroras not only deepens our understanding of Jupiter's magnetic interactions, but also offers a comparative model for studying the magnetic environments of other planets, including Earth. Jupiter's magnetosphere is also home to some of the most dangerous radiation in the solar system. For future exploration, understanding and mitigating these extreme radiation levels will be critical. This has driven advancements in spacecraft design, such as the radiation-hardened electronics used on Juno, which allow instruments to survive and function in this hostile environment. Such technologies will be indispensable for exploring not only Jupiter, but also other high-radiation environments across the cosmos. While the Galilean moons remain the focal point for much of Jupiter's allure, the lesser-known outer moons and ring system also hold tantalizing secrets. Jupiter's faint rings, primarily composed of dust particles, are often overshadowed by the grandeur of Saturn's icy bands. However, these subtle rings provide clues about the small moons that orbit close to Jupiter, whose impacts and interactions contribute to their formation. Studying these rings and their dynamics offers a deeper understanding of the processes shaping not just Jupiter's system, but also planetary ring systems throughout the universe. The outer moons of Jupiter, numbering in the dozens and with highly eccentric orbits, form a population of irregular satellites that challenge our understanding of moon formation. Many of these moons are likely captured asteroids or remnants of larger bodies that were torn apart by Jupiter's gravity. Their varied compositions and orbits suggest a chaotic history of collisions and captures, a history that mirrors the early, tumultuous years of the solar system. Investigating these moons could provide a window into the processes that govern the formation of planets and their satellites on a broader scale. As we look to the future, the potential for artificial intelligence and machine learning in Jupiter exploration grows ever more promising. Autonomous spacecraft, equipped with AI-driven decision-making capabilities, could conduct long-term studies of Jupiter's atmosphere, moons, and magnetic environment without the need for constant human oversight. These advanced systems would allow missions to adapt to unexpected challenges, prioritize scientific opportunities, and extend the reach of exploration into more remote and hazardous regions of the Jupiter system. One particularly ambitious concept involves deploying probes into Jupiter's atmosphere to study its chemical composition and weather systems in unprecedented detail. Such missions would face incredible challenges, including extreme pressure, intense radiation, and powerful winds. However, the data they could provide would be invaluable for understanding not only Jupiter, but also gas giants in general, including exoplanets that may share similar characteristics. Beyond robotic exploration, the prospect of human missions to Jupiter's moons captures the imagination of scientists and space enthusiasts alike. A human presence on Callisto, for example, would mark a historic milestone in space exploration, placing humanity on the doorstep of the outer solar system. From this vantage point, astronauts could conduct detailed studies of Jupiter's moons, monitor its dynamic environment, and serve as pioneers for future missions deeper into the cosmos. The legacy of Jupiter's exploration is also deeply intertwined with our search for answers about life's origins and its potential elsewhere in the universe. The tantalizing possibility of microbial life within Europa's subsurface ocean or Ganymede's buried seas challenges the notion that Earth is unique. If life is found in these alien environments, it would be one of the most transformative discoveries in human history, reshaping our understanding of biology, evolution, and the potential for life beyond Earth. Ultimately, Jupiter serves as a reminder of the interconnectedness of the cosmos. Its gravitational influence, magnetic interactions, and dynamic system of moons mirror the broader processes that have shaped our solar system and others like it. By studying Jupiter, we are not only learning about a distant planet, but also uncovering the universal principles that govern the formation and evolution of worlds. As humanity continues its journey of exploration, Jupiter stands as a beacon of what lies ahead, a vast, complex, and beautiful universe filled with mysteries waiting to be uncovered. The quest to understand Jupiter and its moons is far from over. It is an ongoing story, one that challenges us to push the boundaries of science, technology, and imagination. In this pursuit, we not only uncover the secrets of a distant world, but also deepen our understanding of ourselves, our origins, and our place in the cosmos. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.